Hello? Test, test. Test the mic. Alright. Everything's good. Yep. I can't even hear my typing anymore without a noise cancellation. Okay. Alright, so what's the deal with this stream? We're back. We're back after the disaster of the last one. And I'm still gonna finish that project. It's just I really wanted to work on this one. So I'll do that at a later date. Probably next stream or something. And also a quick goal I want to set is I want to at least stream 1 hour every day. That's very doable. And it'll give me time just to work on stuff that I find fun, and instead of like having to just work on shit all the time. So what are we gonna be building in this stream? Well, we're gonna build a quote-unquote flood simulator. And right now, at least for this stream, there's not gonna be any like rendering with it. It's gonna be straight just back-end logic for it. So, what does a flood simulator mean? Well, say you have a room. This is for our case. It's gonna be very simple, very simple. And on later streams, maybe we can flesh it out if we really want to. But for now, what we're gonna do is we're just gonna test the implementation of it and test that the idea works. So with the flood simulator, what's going to happen is you're going to have a rectangle, right? Now, if there's a source of water coming in, for example, right here, right? This water level will just rise and rise and rise, and then eventually, can I actually go here, take this part of it, and then expand it up? So like it'll go and it'll rise, it'll rise, it'll rise, it'll rise, it'll rise, and it'll rise, and it'll rise. And then it fills up the whole rectangle. Right? That's the like basic idea of it. Now, if we combine it with another rectangle, say for example, it's like a same identical rectangle, same size, whatever. Now say these two are connected, which I'll just signify by this, or I'll just signify by a star, I guess. This means they're connected. So when this water level whoa. So when this water level rises, it's also gonna rise for this one too. So now what's gonna happen is as they both flood, there's a source of water coming, both of them are gonna rise at the same time, right? And we're basically assuming that I don't know. But just imagine this. So now both of them rise at the same time. Not very realistic because it's not how that works, but whatever. Now, imagine if they weren't connected. So if they're not connected, I'll signify this with a... if they're not connected, I'll signify it with a downward thing. So this means they're not connected, right? There's like a door in between them, we can assume. So this means there's a door in between them and the door is closed, right? Now what's going to happen is if this water level rises in this rectangle, now we're just going to assume that it rises at a set rate. Now if this water level rises and it rises and it rises and it rises, this one shouldn't be affected. But, and let's assume that it fills up completely. As soon as this door gets opened, which I'll just mark it as red, which means I'll mark it as green, which means open. Now that both sides are open, what should happen is, and imagine this isn't getting water flooded into it, this water level will start to go down as this room will start to basically fill with water. So now this room will start to fill water, and then they'll basically swap, and then they'll basically level out, probably like 50-50 for like both tanks. So that would be like the case if both rooms filled with water. If like that door was open, and then obviously if we closed this door, and then we were to drain the water out of here, obviously this one wouldn't drain because the door is closed. So we have that relationship of them being connected, and you know, each other's water levels are affecting each door. Now, what would happen if we have that same case, but let's say one of these rectangles, or rooms, whatever you want to call it, one of these rooms is above it, and there's a door. This door is going to be closed. Now, what should happen here is if water was to start flooding into this room, right? If water was to start flooding in this room, we should not see any water go into this other room until it passes this threshold right here. Now, once this starts, so this will rise at the standard rate, and then as soon as it hits here, it's going to start flooding into this room, assuming that the door is open. And then now they will rise. Now these two water levels will rise at the same time. And obviously, if the water source is in this room, meaning that this water is getting pumped in here, it'll only rise up to this level, and then it'll stop. We also will need to support the case if there is, say, a small little room. Let's say there's a small little room down below. Let's say there's a room right here. And I'll just signify this with a cross door. Yeah, that's a door. Looks like one. There you go. So you have this, right? Which is technically a door. And what should happen is water's flowing in here, right? If water's coming into this one, as it would fill, it would first begin to fill this water level. This will fill up. As soon as this fills up all the way, then this one starts to fill up. And then as soon as it hits this one, they will both fill up at the same time. So now these both fill up, and then once it hits here, it'll stop. And then obviously if we had we could have this situation where maybe there's a door behind, but like below it right here. Now what will need to happen is if this were to start filling with water, this would technically need to fill up first, but for us it doesn't. I don't really care. This needs to fill up first, and then this would then need to fill up all the way up to here in order for this to begin filling up. And then as soon as this begins to fill up, you'll get to this level. Then as this rises, then you'll start filling up this rectangle, and then it'll stop around here. And then you could have like a chain of this that like kind of keeps going down, down, down. And the last case would be if there was an above rectangle, kind of. And if there is an above rectangle, like say right here, we can ignore all this for now. Water will go up, And I don't know if this happens in real life, but the water will go and right into this queue and fill this one above it. And the reason why I think that would happen, because I know that this might be really stupid to say that this might not happen in real life, but if you're pumping water into a source, it will fill up this because water's getting directly pumped into it. So yeah. So that's kind of the idea of the project. Is so that I can handle these like situations. But I am really curious about this situation. Does this fill up? Would this box fill up? I don't even know. Am I being stupid? Am I being really stupid? Just look up. Yeah, because you're pumping water into the source, so yeah. That makes sense. Alright. And then just give me 1 second, because once I'm done with this, we'll get started with how I think I'm going to implement it. Figured it out. Got myself a drink. And we're ready to get started. Should be, at least, yeah. Just need to pour my water and we'll be good. After I do that, I'll explain the technicals behind everything. And then we can get started coding. Alright. Go. Alright. So how are we actually going to implement this? Well, my idea, and also again with the last stream, I don't really want to Google anything unless I get really stuck. So we can see how this is, so I can like kind of derive everything myself. Alright, so how are we gonna get this figured out? What, and like also if they're never connected, water would never flow into them. Like quick extra case that I never explained. But how am I going to actually code this? Well, for example, if we had one rectangle, let's just think about this rectangle. What information do we need to store about it? Well, ooh, this font's really big. Well, we'll probably need to know, like, flood rate. Or, yeah. Well, obviously flood rate. I never explained that, but yeah. Where I also want to implement flood rate and let it decrease over time. I'll explain that in a second. For now, let's just get the basics of this idea set in stone. So we're gonna need the flood rate. I don't know what to call this. Floodedness? I don't... What should I call how flooded it is? Like how full it is? Fullness? Is that a word? Fullness? Full size? I don't know. Oh, water. Water. I don't fucking... I'm out of water. Right? Or fullness rate. Full, yeah, sure, full rate. How full it is. Right, that doesn't make a lot of sense, but who cares? I don't know what to call it. Full rate, flood rate, which basically means how fast the water's coming in. Full rate means how much water is in the rectangle, right? How full it is. Fullness meter. I'll just call it full rate. This will be on a value from 0 to 1, or 0 to 1.0. This will be... I don't know. It doesn't matter. Probably from 0.0 to 1, just so we can match. Actually, I don't know, because it depends on how I'm up. We'll think about this in a second. You got the flood rate, you got the full rate, and... what other information are we going to need to know? Well, we're going to need to know its neighbors, which I'll call Neds. For sure, because I don't know, I can't spell, so I can't spell neighbor. Neighbor. No. Neighbor. Neighbor. That was embarrassing. So we need the neighbors, which are basically the connecting rectangles. Full rate, flood rate, neighbors, and then if is source node, or is source. True or false. So, what all this mean? Then this means connected rooms. Oh, I'll just move this like above. This means connected rooms. This means Actually, this doesn't matter, to be honest. Flood rate, I don't know the values yet, so I'll just put that there. But this basically means the rate of water coming into the room. And then this is how full the room is. There you go. So you got the full rate, flood rate, which is basically how fast water's coming into the room, and neighbors, which is basically all the connecting rooms they have. Now, for neighbors, you're going to need to store some extra information. Because here's how I'm thinking about implementing this. So, when your water level is completely zeroed off, right? It's at 0. You have a zero flood rate. Or full rate, sure. I need to think of a better name soon. You obviously have 0, right? It's not full at all. However, if your water gets up to like, let's just call this halfway. Halfway. Well, once you guess, you have 0.5. Oops. Full rate. There you go. Then, obviously, if you're at 1, that means you're completely full. Now, like, why is this useful? Well, obviously, if we want to render, we need to know how full the rectangle is so we can know where to draw the water line, right? But this also plays into the role of when to fill your neighbors, right? And then also flood rate just means how we don't really, right now, there's no like kind of like source of where it comes in. We don't really care about that because it's just a simple draft. If we ever were to render it and we wanted cool like animations or something, we could like we could kind of care about where the direction was coming. But not only is the fullness. What? I hate that fucking name. I don't know what to call it. I need to ask ChatGPT for names, bro. I have no fucking I don't like that. What are some variable names I can give to something, or what are some variable names I can use to represent how full a rectangle is of water on a 0 to 1.0 scale? Oh wow, yeah, that's obviously way better. Damn, I need a ChatGPT that could come up with that for me. The fuck up. Oh, bro, what? How did I not think of that? Bro, okay, so ChatGPT came up with a great idea to call this water level. The most fucking obvious water level. Water level. There you go. Load that. Aw, you mother. Okay, I'll just shrink the size. Hope no one has OCD. Because if you're OCD and you're watching this, it's gonna piss you off. There you go. Water level. This basically represents how high the water is. Now, why is that important? I never explained it. Because if you have a neighbor, for example, let's draw the case of a neighbor. These two neighbors are connected, right? How are we gonna know when we should fill up this rectangle over here? How are we gonna know, like, if this is getting filled up right? If this is getting filled up right here, how are we gonna know when to fill up their neighboring rectangle? Well, we can use the fill or the water level to kind of just explain at what water level our current room has to be for this next room to start getting filled up. Now, because what that means is it's going to handle this case, where if this water's filling up, how are we going to know when should we start filling this water, room up? Because if we're filling this room up until it passes, like, this line right here, this room shouldn't fill up with water, right? But so we can use this to be like, okay, well, once this room hits 0.3 water level, right? This is like basically 0.3, which is like roughly right here. Once we hit that level, we can start filling up this room right here, and then they can both rise together. So the water level can also tell us when, when to start updating our neighbors, when to start flooding our neighboring rooms, which is like the key idea that kind of makes this thing work. Flood rate obviously is how much water is coming into the room. Now, why is that important? Well, because every tick or every iteration, every run of the simulation, we need to know how much water should we pump into this rectangle. We're also going to assume first that you can't close. There's no doors or nothing yet. I mean, this should be a simple boolean called is door closed, blah blah blah, and then that should be fine. Which would be stored in the relation. So now we need to store some more information about our neighbors. Well, what information do we need to store? Well, we need to know basically the sorry, one second, I got distracted. We basically need to know, like, what water level do we need to start filling up that rectangle. Which I'll just call required or min water level. Which basically means water level needed to flood this room. Alright, makes sense. And this will again be on the I don't like that. I thought that would make it look nicer, but I didn't. Which this would be on the scale from 0.0 to 1.1. Alright, same thing as our water level. We also need to know what we need to know. Because if you have two water sources coming in, well, that doesn't matter. You need to know the min water required to fill the room. We also need to know, I'll just say max water level, which basically means how much our room can fill them up. How much our room can fill this room up. Because the reason why we need to know that is because I do want to implement a feature where, say you're having a stream of fluid. Right here, I'll just draw it. Say I have a stream of water coming in at one rate per second per tick. So like this room would basically fill up instantly, kind of. If I make the water rate on a scale of 1. This would fill up in like 1 tick. Right? Or like 1 iteration, like 1 time. Because I'll probably keep a variable called time that we can keep track of. But that's important because I don't want, if you have multiple rooms, right? If you have multiple rooms and there's only one source of water coming in, your water rate shouldn't be able to flow by 1 into every single room. Technically, the effect should damper. So maybe here, I don't know the rate that we should use, but maybe here it would be 0.5 coming in, and it would be 0.5 here. I know my handwriting's terrible, coming in here. So while this room's getting pumped with 1, rate of 1, it's also losing water at 0.5 here, 0.5 here. Which will basically, kind of like, almost like, it like acts as time, kind of. Because when you fill up water right here, this room If they're all... Bro, I don't know how to articulate my words. Oh my goodness, what am I doing? You get the point. It's kind of, I don't know how to explain it. It seems like common sense. If water is flowing into here and it has to go to other sources, obviously it's going to get, like, damper because you're sharing. You're basically sharing one stream of input. So if you're taking one stream and you got to split that stream off, obviously it's going to have a dampered effect. It's the best way I can explain it. Now, why is that important? Well, because we need to max water level. We need to know when has this box been filled up to our, like, max potential. So for example, here with this room, we could fill up this entire water, like we can fill up this entire water source. Say this is getting a stream of 1. We could fill up this entire water source and then have this much water in our tank, because that's just how the water level will work. But once we hit, like, here, say we have a rectangle up here, we don't want to be, once we start filling up this rectangle with water, we don't want to have the same negative effects as right here, right? Because this is full. Our stream of water is not going into this room anymore. Like, it's not going in here anymore because it's already full. You're not pumping any water. So this should have a higher rate of flow coming in, right? Whereas, like, if we did it before, say, like, this gets dampened, so 0.875, I would say 0. Like, this, it would be this much rate coming in, this would be this much rate coming in here. But if you split that off, because here's what I'm thinking. Actually, let me try to explain how I want this water flow to work. Say you have a stream of 1 coming in. Automatically, what's going to happen is you're going to lose a certain amount of flow. Maybe if I really want to make it more complicated, right? And we could have different size rectangles and all this stuff. Distance could play a factor in it. But for now, I'm not really thinking about that. But, like, in real life, as you travel along this rectangle, your flow of water becomes slower as you, like, travel, because you're getting farther away from the source, basically, right? The source is strongest at its base. So automatically, before you transfer, you're going to lose some water rate. So for example, when we go to affect this box and this box, obviously I deleted this one. They would have it would actually be better drawing if I whatever. I was gonna say it would make more sense if I drew it, like, flat, but like, honestly, who cares? But, like, you would automatically have this water rate kind of dimmed. It already kind of loses effect because it has to technically travel over the rectangle. So we'll just put it at 875. Now, imagine for some reason these were both being filled up at the same time. For example, if I had water coming down here and I had a tank right here, and I had a tank, this is actually, like, smart. If I had a tank right here, oh, fuck that, I'll just do this. Boom, move this here. I hate paint sometimes, I'm not gonna lie. Delete. You can delete this. There you go. Whatever. There you go. Imagine if I had, like, this, right? What would happen is obviously if it had travel over time, like, we're just assuming that, like, the water rate shouldn't be 1 for both these rectangles. Right, so we should dim it just a little bit. But now both these rectangles at the same time are going to be taking 0.87, like, water. Right? Or I'll just put 0.9. That's just simpler to, like, understand. Like, they're taking... That's their water flow coming in. That was terrible now. Whatever, 0.9. But technically, we should also, like, negatively impact this, too. Because now your water source is getting split off into 2 more directions. So technically, the water source, if you're doing 0.9, I don't know how much we should affect this by, but it should get affected. Where, in actuality, this might be getting, like, for a simple case, we'll just say this is getting like 0.45, and this would be getting 0.5. Let's just split it down the middle. So as like you have to share the same water source, you lose the amount of water coming in. Like, obviously, it's just how it works. But the reason why we need to know the max water level, which is how much we can fill this rectangle by, is because if this tank becomes filled, say this tank becomes filled, technically this, oh yeah, this one would become filled first. And like this one would start filling because like now we have this one completely filled, and now the water can start moving up in level. We shouldn't still be having this negative impact. Like, this negative impact should not be happening because water is actually not going there. It's not flowing anywhere. What is actually happening is that has been taken away from this once it's full, and it's moving to go and fill this one up as much as it can. So this one should then fill faster because this one is already filled. I'm basically sitting here and explaining, like, looking common sense. But, yeah. And, like, I'm explaining common sense in, like, the worst way possible. But yeah, so, but we need to know how much we can fill it by, because imagine if we had, the hell? Oh, okay, imagine if we had, like, a, let's first say, we had maybe, like, this rectangle. Actually, depending on how the rectangle is formatted, how would I actually... make that possible? I'm trying to think of a case where this would be, because like the way currently how this works is like technically this entire like section, anything like a lining would be its shared value. Like this, there's like no door system. Okay. Will this ever be an issue? Like fill level, where we would need to know that we could only fill it up to a certain amount, because technically we're only doing rectangles. We're not going to worry about making complex shapes or nothing, where like you can have like, I don't know, a triangle, or you could have like a shape that looks like this, where like this would be an air pocket if water was coming in right here, because right now we're just focusing on rectangles. So technically we wouldn't actually have to worry about that. I don't know. Actually, I kind of stumped myself, so I'll hold this off. Now, we might not actually need to know that. Alright. So you get the point. I want the ability for one, like a water source to come in. I want it so as you connect rectangles to it, these will get filled up if they're lower. They fill up at a certain size. They'll start filling up at a certain water level, so you don't have like weird issues coming in where this one's filling up down here. It's filling up at this level, but this is also filling up at the same time. That doesn't make any sense. And yeah, I think I explained it enough. Hopefully. So let's actually get into the details of how I actually want to implement this in the code. Well, and I might actually have to think about this like a lot harder. Maybe I should plan it out like fully before we start coding it, but I don't really care. Technically, at least in my mind, and again, I'm going to reiterate, I've not done any research on how these are actually implemented in video games or how they're implemented before. This is all just from my head. To me, these are just graphs, right? Technically, each rectangle is a node in a graph. So the way you can think about this is, let's say that this is node 1, this is node 2, this is node 3, and this is node 4. So you would have 3 nodes, 1, 2, 3, and 4. So 1, 2, 3, 4. Now, are they connected to each other? And when they're connected, they're going to be bidirectionally, like there's no direction in the graph. It's directionless. Because water can flow in both directions. There's no way that water is just only going to flow here. And it won't flow back out if anything happens. That doesn't make any sense. Water will be bidirectional. So, technically, this is how it would look. If I take these nodes, 2 is connected to 1, 3, and 4. It's like a tree, basically. And again, and these aren't connected, we'll assume. Like, just imagine there's some space there. These aren't connected. But they're connected, but 1, 3, and 4 aren't connected to anything else. But if I were to take, let's say, like, if I were to create like a rectangle right here, you can call this 5. Then 5 is now connected to 4. Then, and you can kind of see how this can grow. And then imagine if, and then we can have like a more complicated example where we would have this down here. This would be 6, but 6 is actually connected right here. There's a door right here, and there's a door right here. So 6 is actually connected to 4 and 3. So 6 would be connected to 4 and 3. Which, I mean, there's probably an easier way to draw this graph, but yeah. And these, like, connections, because, like, right now, if I were to make 2 a water source, which basically means we're flooding water into right here, what would happen is obviously it would go to every single one of these nodes, because 2 is connected to all these nodes, like, no matter what. So if 2 was a water source, technically all nodes would be connected to each other, right? Unless you were to, take like, come on, oh, that's dumb. Unless you were to like have a fully disconnected rectangle right here, which would obviously be connected to nothing. Because if you were to start flooding 6, technically all these are connected to each other, and so if any of these water nodes became a source of water, eventually all these would begin to flood, and at different times at different rates. However, in reality, they won't all just fill up to like 100%, because each one of these, and they won't all fill up at the same time, because each one of these like nodes affects each other node at a different rate. So for example, if 2 were to become a water source, it would affect this one pretty strong, it would affect this one pretty strong, it would affect this one pretty strong. Then you would have, and then as 2 goes, well, 2 wouldn't really affect this one at all, because it's a little far. And 4 would also affect it at the same time. And then 4 would also go and affect this one. So like as you go farther and farther away from the water source, the less effect it would have. And this would be technically the amount of water rate coming in. So for example, if I want to split this up, I guess 1 will just have like 0.3, coming in at each one of these rates, right? And like 0.3, and then you have to like split it up as water would leave. And then this would obviously, now this has a flow of water coming in at 0.3, but now this has to split it up between 2 different nodes, so this would be like 0.125, this would be, where the fuck did I get 1.125 from? It'd be 0.15, 0.15, right? This would obviously, and then obviously there would be like a damper effect to this too, so technically they wouldn't be directly half, they would be, less and less because you're traveling over a distance. And they would all get affected at like different, so they would flood at different rates. Give me 1 second, I have something here I take care of. Alright. I'm back. Alright, so let me explain, like, why this actually, like, is a little bit more than you'd probably think. Like, this is pretty simple. You have, like, the case where, like, two come in and stuff. But, like, with this, like, representation of, like, nodes, how do we know when should we fill up a certain node? At what rate should we fill up that node? And other stuff like that. Well, we can use the things, the variables, like the one variable I said earlier, right? Which is the min water level it would need to start being filled up. So, for example, when we do 2, which I wish I could, like, I wish there's a way I could just clean reset this shit. Here, I'll just redraw the graph, I guess. Okay, so you'd have 2 connects to 1, which connects to, what is 3? What does 3 connect to? Well, 3 will connect to 6, and then 4, so, 3, then 4, which, does 3 connect to 4? No, but both connect to 6, and then 4 connects to 5. There you go, that's a little bit cleaner. So this would be kind of like what the graph would look like. 5 goes to 4, 3, 4 go to 6, 4 also goes to 5, and stuff like that. Now, the barrier for entry to 1 is water level 0, right? Would be water level 0, because as soon as, like, we get water in this tank, we're gonna need to go and dump it into here. Same thing for 3. So with the barrier to entry, which I'll mark as this red, which is barrier to entry, for 1, we know we can traverse it if our current water level is 0, 0. It's like the first requirement of this. That looks like a fucking stupid ass face, but if it's 0, we can traverse this, right? For 3, we also can traverse it if our current level is 0. That's like the first line that we need to know. But for 4, we can say that this is kind of like at the water level of, if I put my 0.5 mark right here, this is probably like 0.4. This water level needs to be at 0.4 in order for it to start flooding, for like us to actually implement a rate of change. So this barrier to entry is actually 0, just say 0.4. Right? So before we can even, like, start, which I'll just mark this as blue for source node. So for this source node to even start affecting these other nodes, we need to first pass this test, which is, what is the barrier to entry? Which means, what is the water level this node is required to have for us to, you know, actually go and affect these nodes? Well, for 1 and 3, we don't need anything. We don't need any water level. So we can just immediately start filling up these nodes. However, for 4, we need a water level of 0.4 before we can even start affecting them. So the way this simulation would play out with this current knowledge is at, and I'll just make like a chart, which this is time, and this is it's fucking time. And I'll just mark it as for time 1, this would be that. For time 2, it would be pink. And then for time 3, it would be like green. I don't know. That's really terrible colors. Those are ugly as fuck. But as time were to progress, let's say the first iteration of time. Well, the first iteration of time, let's say that this node gets filled up. And right now, for example, I'm just going to ignore this shit because it'll make it more complicated to explain what's happening. At time 1, maybe this will be filled up halfway, for example. And then at time 1 for here, this is obviously filled up at halfway. Now at time 2, let's say this got filled up and this got filled up. And then let's say now that these 2 are filled up, this also somehow got filled up just a little bit. Now at time 3, what can happen is we can start now filling up node 4. And that's basically how it would change. That's how it's not as simple as just, okay, you just basically, because any like containers, technically, they're all connected. So in reality, all you're doing is just filling up all the nodes at the same rate. But to make it actually like work like in kind of like real life, which isn't real life, but kind of, you need this like barrier entry to simulate how this functionality works, right? Which means, because if we were to put water in this rectangle, not all these rectangles would fill up at the same time. It's just not how it fucking works. But with this behavior, we can kind of simulate that better. Now, again, at 3 needs a barrier, let's just say, that's kind of like similar to us over here, so let's just say like 0.4. Well, for 3 to start filling up this rectangle, we would need to fill this, we need 0.4 water level to start filling up this one. For 4 would need a 0. 4 would need 0. And for 5 at 4 would need fucking 0.4 again. Damn, I drew them all not at like half. Whatever. I'll just say 0.5 to like mix it up. Whatever. There you go. So these are like kind of all like the barrier to entry. So if I were to ask you the question, okay, well, which node would get filled up first? Well, obviously, this one. But again, this works in the opposite direction too, right? Because this isn't directed. If this was directed, it would be, okay, there you go, there you go, there you go, right? Which, let me actually think. Do I want it to be directed like that? Because that'll make it a lot more simple. Ooh, let me think about this. Because basically you should point the direction of where the water is flowing, right? So if 2 is the source node, water would flow here, 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 then it would go to here, then it would also, this node would also assist it, and this node would also assist it, right? Because technically 4 wouldn't send water towards you. Both directions, then things could get kind of weird. Well, what do you think about that? Oh my god, I forgot to start the same fucking work timer again. There you go, an hour late again. Whatever. Okay, so what I'm like talking about right now is maybe we want the graph to actually be directed. And like that would kind of contradict what I said earlier, where we said we didn't want it to be because water can flow in both directions. But we're kind of talking about we're pumping water into the system, right? Which means we're pumping about like a rate of 1 flow into this into this node right here. And we basically need to distribute this down this chain, right? Because no water, unless like, technically what would happen is say we filled this node up and like we had doors or something or shit was closed, this would be a source, because then if your other water is not empty, then it would flow in. But because technically if we made, if currently, because I want to think about this, because if like down the line we added the functionality where we can have doors, right, in our simulation, say that this door is closed, this is closed, and this is closed, and this was filled with water, what would happen if we open this door? Well, all the water would flow out to here, but currently, and then like, and we can still say 2 is like a open source of water. I mean, technically what we could do is we can just say, we could like kind of reconstruct the graph at the same time, because if these doors are closed and they're not connected to each other, I don't know. Because the reason why I wouldn't want to, why I'm kind of like hesitant on doing that is because I'm like thinking like I would have to adjust the graph at real time as the simulation changed, but I think that's kind of normal. But this makes the most sense. Okay, whatever. I'm not gonna worry about that just yet because I'm overcomplicating the problem. I just want to get this simple idea done, right? And with this simple idea, this like one-way direction where you just point wherever the flow of water is going works, right? Where if 2 is the source node, water would flow down to here, to here, to here, to here, and to here. Right? Now, we need to also, with this, like, barrier to entry, this also simulates what water level it needs to be at for this rectangle to start filling. However, we also need to make it so that like the source rectangle, like we can know when we can start filling up our own rectangle, right? And what I mean by that is, say that this rectangle is getting filled up with water. From the graph, we said that these 2 nodes, immediately after we start filling these up, I'll draw this in a different color, and also I might like erase this too. Oh my goodness. There you go. Okay, so if we made this the source, right? Water's getting pumped into the system right here, into this room, right? Well, immediately from our graph, we said that we need to start filling up 0 and 3 instantly because they're at like base water level. Like they instantly need to get filled up. So this rectangle technically shouldn't be getting filled up at all because these 2 need to start filling with water. However, we need to know when we can start actually increasing this value on our own rectangle. Because what's going to happen here is when this rectangle fills up, which I hope I can like just delete this. The way this would work in like a simulation is if we start filling this up, water will go into here. And this will get filled up first. Because it's at like a lower like its top is lower down on the source rectangle. Right? Which means that by the time we get to here, and this rectangle gets to here, right, which is how it would work. I cannot draw a straight line to save my life, what the hell? Once, like, these water levels get to this point in their rectangle, we know we can begin to fill up our own rectangle now. Right? Now we can begin to fill this up because these 2 are satisfied. They're at the same, like, almost, they're at the same water level, technically. On the whole system. Now these can begin to fill up, which then gets stopped when we encounter. Which what I'll do to make this actually simpler and like easier to demonstrate is I'll take all this shit, I'll move it down to here, and then what I'll do is I'll take this and I'll move it up just a tad. There you go. There you go, bucko. There you go. So now what can happen is once these reach this level, which for this node would probably be like, what do you guys think? 0.8? 0.8 water level? This is probably like 0.4. No, because half is like right here. We'll do like we'll just do 0.4. Once this node gets to 0.4 and this node gets to 0.8, we can then begin to start filling up. We can then begin to start increasing the water level here because this is satisfied, which will then result into this node getting completely filled, us getting up to this level, and then once we hit this level again, which is probably like for this node, like halfway basically, we can start raising this level, and then again we can continue going up and up, because what will happen is this one's going to start getting filled, and then, you know, that's just how it's going to flow. But how am I going to tell the source rectangle that, or other rectangles that are distributing water, when they can begin to fill up? When is that actually the case? Well, I don't know. I'll have to think about it. Well, we could store information about, which, let me clear up this entire drawing. We can store information about what water level this will need to be at to be lined up with whatever water level we started at. So, for example, the starting fill line, like the minimum water, is 0 for this node. So this rectangle has to be at 0 for this to begin filled up. However, the simplest way to begin to fill up our own rectangle is to be like, okay, well, once this node is completely filled with water, then we can begin to fill this node up. But that kind of breaks the simulation, because this node should start to fill up once it passes, per se, 0.8. So some information we can store about like a node is what level, like what's the base level at? Like where do these two nodes connect? Which for our case, this will connect to this node at 0.8, and this node will connect to this node at, or this node, this rectangle will connect to this one at 0, and this rectangle will connect to this one at 0.8. So once this connection reaches 0.8, we know that we can fill up this node. And then we could do that for every other node. And then obviously you'd fill up a rectangle once you know all its neighbors have reached the water level where you could fill up yourself. They reach the minimum water level that you can satisfy without putting water into your own system. Right now, I'm just thinking. I'd pause there for a second because I'm thinking like, okay, well, I keep thinking about the doors thing. Are we gonna add doors? Are we gonna add doors into the thing? Well, if we add doors, what would happen is, say this is all blocked off. If I started 5 as this, it would go down to here, go down to here, and it would go down to here. Or if this was blocked off and this was the source, it would go down to here. I don't know. I'm overcomplicating that. We're not gonna worry about that because technically all we need to do is just redirect. We just need to redirect our graph, which hopefully we can make fast. So, back on topic to this, I think the solution would be to just store information about when is this water level matched. Like, when have these two values effectively matched each other? Like, in relation to each other. When has that happened? For this case, this would be 0, right? For this one, it would be 0. And it would be, for this one, it would be like 0.3. Once this water level hits 0.3, this one has hit 0.8, we know we can start filling this up because we have no more dependencies. And we have nothing else like taking away our water. Once these two values have been reached, these two neighboring tanks, we can begin to increase the water level from this rectangle. And I'm almost thinking that this is going to be like almost recursive, so it doesn't matter. It doesn't matter that we don't know anything about this neighbor or this neighbor, because if we do this logic for every single rectangle or every single room, this will be handled throughout the entire simulation. Because again, this water level wouldn't be filled up until, like, say that this was lower than say we had an example of, ooh, what the hell? Oh, say we had an example of this being the source, this going down to here, and this going down to here. Well, and then like, let's say like, there's like a node right here. Well, we wouldn't have to worry about us knowing any information about this because this this cell wouldn't even fill up to match up to this level until this one's filled up, and then this one goes up, because it's almost recursive. If we do this logic for every single cell, we don't have to worry about any future cells. We only have to worry about our nearby neighbors. I am making this in Python because it'll definitely be the easiest to like prototype in and probably the fastest. And then if I like feel like we need more speed or something, I could move it either to. I'd probably move it either to Go or C++. But for now, since I just want to make like the most like simple prototype, see if I even like have enough fucking knowledge to do it, I'm just gonna make it in Python really quick, throw something together. And yeah, I probably wouldn't even need to move it to Go in a C++ because I'm not planning on handling really complex, like big complex systems yet. So, but that would be cool if I can prove that this works with like small situations with Python. And I wanted to start handling bigger situations. I would definitely move the language to a different language, because I would bet that Python would slow down. Because at least from what I'm looking at right now is if we introduce new source nodes and if we introduce like different ways to configure the simulation, we would have to do like graph redirections, and if it's really a really big system, then it can like kind of bog it down. Or I could just become smarter and come up with a better solution where we don't have to do graph redirections. But yeah, PYQT. So it's called. If you had a Discord or something, I would love to join and see the files all. Unfortunately, I don't have a Discord made because I've never had like demand for Discord yet. On like YouTube. The best way to keep updated with it, like especially since I don't have a Discord, or if you want to like know if a Discord gets made for any of my projects or any of my stuff, just keep updated with see if I go live, because this is all gonna be on live. I'm only gonna code on this when I'm live, so you can always come back to live streams and watch and see the progress. And then you can always keep updated with the community tab, because if I ever were to make a Discord or something like that where you guys can keep updated, I would definitely update the community tab first, and then there you would see all the updates and if I made a Discord and all that stuff. Thank you for subscribing too. It popped up on my Windows thing, which I don't know how to turn that off. I don't want notification. This is annoying. I hate how that pops up on stream, because sometimes if something really sensitive popped up, that'd be really annoying. But what is PyQt? I've never heard of that. Oh, coding Python binding for Qt. I've never heard of this, to be honest. Cross-platform GUI toolkit Qt implemented as a Python plugin. Yeah, I've not really Google settings with YouTube. Yeah. It from what I'm reading, yeah, it makes GUIs. Currently, I don't even know how I'm gonna render this. Right now, I'm just doing like raw data, just manipulating the raw data. Because I can understand what's happening if I just print out the values and the water levels. I'll be able to understand what's happening. I don't need visuals or nothing until I can prove it works, and then visuals later. So I don't really use a lot of like Python libraries, to be honest. Yeah, I will. There will be math. It shouldn't be too advanced. It's not gonna. I don't think it would be too complicated. It's not very complicated math. Because I have like, there's gonna be a math function I have to make which like dims out or like reduces how much water goes into a system based off the connecting neighbors and how many like of them are taking in water currently and stuff like that. Yeah. Especially if the water is constant, like you said, yeah, it would really only be algebra. Yeah, I really like coding too, but I've been trying to figure out ways to implement math more into my code. Because I do like math, and I really want to figure out how to implement complicated math systems in the code, so. Alright, man, thanks for joining. Hopefully you have good luck on your study, and you can keep updated with me on the lives and everything, and I hope I see you again sometime. And hopefully this goes well. I can show you guys something. Alright. Yes, I'm going to use Python for the rough implementation of it, and then if it can't handle big systems, I'll have to either optimize it or switch language. Okay, so let me get back on track. So the solution to that issue would be to store basically what level these nodes are connected on, and how would you get that information? It would be you could check the node and then oh goodness, how am I going to implement this? Because right now we have nodes, and each node will store information about itself, right? But this is only information related to the node. It has no information about who it's connected to and what that relation's like. And then we have the flow graph, which the flow graph basically would represent how water would flow in the system. So each node is basically like a rectangle. Obviously, that's what it fucking is. And we could have a list of nodes which basically explain the rectangle and its state. And we could have maybe two graphs where we have one graph which represents how nodes are connected to each other. So for example, we would have 5 and 6. Then just get added. So what would happen here is our connection graph would look something like this. And since it's a connection graph, I can actually make it look a lot nicer. So we'd have 2, 3, 6. Okay, no, that's terrible. 6 should go here, and then 4. The 4 would then go to 5, and then 2 would go to 1. So this could be like what the connection graph looks like. And again, this connection graph doesn't have needed direction because it's literally just showing who's connected to who. Like, what is the structure of the map, basically. So this would represent, like, basically the rooms and how they're connected to each other. So obviously room 1 can only go to room 2, which we can see right here. Over here, 2 can go to 3 and 4, which makes sense. That adds up, 3 and 4. 3 goes to 6, right? 6 can go to 4, but it can also go to 6, right? It can go to both directions. If you were to look at 6, it can go here and it can go here, right? That's why it needs to be, it needs to handle both directions, right? And then 4, obviously, 4 can go to 2, or it could go to 6, or it could go to 5. So that's why it has 3 nodes that it can go to. Now, with this graph, which I can call the structure graph, I don't know, I'll call this the map graph. For the map graph, we can store information, these directions, which I'll draw like this. This basically stores structure information. Oh my goodness, type information about their connection. There you go. So this line, which is basically the connection, basically tells you information about it. So this could include what level, basically, what level do they meet at. But that's basically, like, currently the only thing I know that they need to store. So, for example, 1, I'll draw this at the top. So 1 would go to, which, so 1, like, this would represent, like, this red represents, like, this connection. There you go. If you see red, that means this way, and if you see blue, it would go, this way. It would go in the opposite of red. That's basically what that means. There you go. So, for red, these two would probably connect. So 1 lines up with 2 at 0.8. Okay? Which we'll use kind of like the water level to explain what they level up at. For 2, yeah, 2 would connect to 1 at 0. Connects to 1 at 0, right? Because that's where they meet. And we're not worried about that. We're just literally worried about, like, kind of like this value right here. Like, these connection points. And, I mean, which is, like, so, like, the bottommost connection point is what we're worried about. Because right here, technically, they have 2 connection points, but we're worried about the lowest one. Like, what is the lowest connection point? That's kind of how it's going to work, because water rises up and stuff like that. So, worried about the lowest. I don't know if that'll be an issue. I don't think it'll be an issue. Well, 2 will, but, yeah, so we can go back to building this. 2 can connect to 3 at 0. Well, 3 connects to 2 at, we said 0.3. 3 connects to 6 at 0.5, basically. And 6 connects to 3 at 0. Right? Because they're lined up right here. So 0, they connect for 6 at 0, for here at, whatever, you get what I'm trying to say. 6 connects to 4 at 0.4, I guess we'll just say. And then 4 would connect to 6 at 0. Or, yeah, right? Yeah, 0. And then 4 connects to 5 at, like, half its speed. And then you have 5, which connects to 4 at 0. Now, you can kind of see a pattern here, whereas we have one direction, which goes to 0.8, and if we have that, the returning result is 0 every time. You can see here, 0.8, and then it receives a 0. This is 0, so it receives a 0.3. This here is 0.5, this returns 0. Why is that the case? It's because what I'm doing to simulate this is there's no information about, like, their wall. Technically, what's happening here is this looks like this. It looks like this, okay? And this would look like this. This would look like this. This would look like this, and this matches up. So what's happening here is there's no, like, wall right here. There's no, like, overhead wall, which can, like, artificially raise this, like, the starting point, their connection point. Because technically, if I were to add this, like, wall right here, these would be connected at 0 at a different point. Where 6 would connect to 0.4 at, like, now, like, 0.6, and then 4 would connect here at, like, probably, like, 0.1 of its value. So I don't have, like, support for walls or anything. But I can add that. Now with this feature, as long as we store that, we can have this feature where they would also store, like, their returning value, which is basically like, okay, for me to go here, it's 0.8. For me to go here, it's 0.1, or it's this percentage of my fill. But this is basically the map graph, which can kind of give us this information. So we could store basically like this, and then we could search this graph to basically know the information we're trying to get from here. Which, if I look at this again, if you take, and I say if I make any of these nodes a source node, if I make this a source node right here, we can begin filling this up at 0. We can begin filling this up at, what is this travel line? Oh, I never wrote it, did I? 4 connects to 2 at, oh wait, it literally happened right here. 4 connects to 2 at, its 0th level, and 2 connects to 4 at its 0.4, like, level. Well, now, actually, now that I think about it, if we just store this, like, map data, which is basically, like, the structure of our map. I literally just said that. Why do I keep repeating myself? Map data, structure of map, same shit. If we were to make this a source node, well, we can just follow this direction. We can follow up here. Okay, we can follow here, or we can follow here. Well, we can only follow here if we have a source of 0, which we do, so we could follow, start filling this up. And then we could go here at 0 too. So then the water would go here, it'd split off to right here. This would split off to here because this is 0. This won't begin to fill this until 0.3. This would go here, and this would go here. And we can kind of use this to kind of tell. So if I were to make 5 a source node, we could look at this graph and travel, like almost do like kind of like a, I don't know if it would be, I mean basically Dijkstra's, right? And just travel along the shortest cost, which is 0, 0, 0. The water will follow kind of the least resistant path, so it goes 0, 0, 0, and if so we would make this node our source node, container 1 would be filled up first. Why? Because here, 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 this would begin to fill up first. Then if you travel along this would begin to fill up here. And for our case, for our case, I won't assume that there's like time delay between there's like no delay in how fast it would fill up. Like I just kind of say the water moves really fast. I mean, I can add time delay, which I mean I can kind of simulate time delay by just that drop-off function that I was talking about earlier. But this would begin to fill up, and then assuming that they fill up the same rate, which technically they won't, because at least for right now, all the rectangles are going to be the same size, right? There's not going to be difference in heights, so they would fill up at the same time, which would then result in this one being filled up first. Obviously, it would be more complicated to figure that out if we made it so rectangles would be different heights, because then you would, you know, need to like translate it into account that fact. But if they're all the same height, which means they fill up all at the same rate depending on the water flow, this would technically get filled up first. But again, if we assume that I'm doing a thing where I drop off the rate of flow, technically the rate of flow would happen here, because you only drop off a certain amount. Let's just look at it. If you fill up this node, water will go down to here, which would also go to 6. Did I mark that? Yeah, it would go to 6. And then this would go to 2. So it would go off to here. Oh, I didn't even look at this. So water would have to go off to both these directions, because this would travel along 0, this would travel along 0, which would split up to this. So technically this would fill up first, because you're getting input from here, and you're getting input from here. Because if you watch the water, it would fall down to here. If this was water coming down, it would go here, fall off into here, go into here. This would fall down, fall down to here. And then this would go and fall down into here. And technically this would be getting the most water. But it actually wouldn't fill up first, because technically this would need to be filled up, and then, yeah. But the simulation would tell me that. Because again, with the logic that we laid out, which means that other cells can't fill up until they get this level. Yeah, I'm kind of like just rambling. I know that this makes no fucking sense, but yeah. Maybe I should simplify the example to kind of test my logic. That's always a good thing to do. Don't always give yourself the most complicated example. So for this case, we'd have 1, we had 2. Our structure graph would look like this. Here you go. And obviously 1 would connect to here at like 0.8. So if you're traveling this direction, it would connect there. If you're traveling this direction, it would be, if you're going from 2 to 1, it would be at level 0. Right? Because you need this water for this to go down. Which makes sense, because if you were to start here, if this water source were to start here, you have to go down to here. If this starts here, you have to get up to this level in order to begin to travel to here. Now, we can like kind of test and we can see, okay, if we make this water the first, it would go to 1 at this, but if we made this would fill up to 0.8 and then start watering here, which makes sense, right? But what I want to do is, so this case is simple. Say I made 2 the water source. Well, 2 wouldn't get any water added to itself until this filled up to 0.8, which means this like returning factor comes in. And then this can be like, okay, I have to wait till 0.8 in order to start filling up once this condition is true, and then this can begin filling up itself. Now if I were to add in, please stop. If I were to add in this container, which would be basically the same exact copy as number 1, which is number 3. If I were to add this, I'll just delete this. There you go. So we have 2, which goes to 1, which goes to 3. It's like a tree. Again, 1 connects at 0.8, 2 connects at 0, 2 connects at 0 here, this connects to 0.8. Right. Or, I mean, maybe I want to make that look cleaner. So I'll just draw it out longer. So this goes to 1, this would go to 3. If you were to travel up this direction, 3 would need to go to 0.8 in order to travel up here. 1 would need to go up here to 0.8 still, and to go down here, it would need to be... Actually, I can just do this. Boom, boom. For this to go down here, you would need 0, and you would need 0. Let me also vary this. So, let me actually vary this. This, we'll say, is 0.5. So this is 0.5. And let me actually move this up to like represent that. That's probably like halfway. So if you have this, how is the water going to flow if I were to make 2 the source direction? Well, we know that, okay, if I were to make this happen, water would go down here to here and to here instantly. Like instantly, because this takes 0, right? Which is represented by our graph. If we made this the source, go down to 0 here, go down to 0 here. Now, this would begin to fill up. And this would begin to fill up. But for our case, 3 would fill up faster than 2, because basically this is 0.5 right here, right? We said that earlier, that this is 0.5 connection point, and this is 0.8. So once they reach halfway, both containers would reach halfway, technically. This 3 is going to start overspilling into 2, which basically means we can't raise level 2, because once any water going into here is actually getting redirected to over here, right? Because if you were to try to keep raising this water would begin to trickle and then honestly flow down here, right? So this now an input would go into here, but how would we actually simulate that in code? And then obviously after this, so both these would begin to flow into here once 3 reaches 0.5. And then once 1 reaches 0.8, we can raise the water levels at the same time, which means we can raise this too. But how do we actually write the code to do that? What would be kind of the idea here? I have no idea, to be honest. For now, we know. We'll actually have to implement our flow, our rate of flow into this. I'll actually have to think about this now. So if I begin this 2, if I begin to fill this up with 2, and for now I'll just say that to make this simple, we'll just say that water fills up everything at an even rate. No matter how far you travel, how far this happens, water will fill everything up at the same rate. You do not lose the rate of flow of your water, like how I was explaining earlier in the video. You don't lose your rate of water flow, because that makes the problem simpler to deal with. So let's just say I pump into this system a flow rate of 1. Well, this is 2. Now what's going to happen is the water is going to follow the path of least resistance, which turns out that it's going to be this one and this one, right? So water will then go and travel down to here at a flow rate of 1, because again, we're assuming that we're not losing the rate of flow. Now, this node knows that it has an incoming source of 1, and so its output source would also be 1. So its output source is going to be 1. And you can see this is where this could become an issue if you get kind of, because this is a cycle, but nevertheless. But what's gonna happen here, well, we won't even think about that yet, is the water's coming in here at this rate at 1, this is coming here at this rate at 1, which means, and then obviously they don't have anywhere else to fill up, which we can determine by what? How can we determine whether or not we can begin to fill a node? Because technically this problem would then be sent down to this node. So let's just think about one node. Let's just isolate one node, and we're pumping a rate of 1 water into it. We're pumping 1 water rate into it. To make it actually look like a 1, we'll just say 2, because it looks 2. There you go. We're pumping 2 flow of water into this node. How do we know that this node can actually be like, okay, it's time for me to raise my own water level? It's not time for me to go and distribute it somewhere, because I have no neighbors. How are we going to know that? Well, obviously the first base case is no neighbors. I'll just call it nip. So you spell neighbors, right? I forgot. I don't know how to spell neighbors. No, that is not how you spell neighbors. Jesus. No one saw that. There you go. No neighbors. I'll just call it no connections, okay? No connections. I'll just call this cons. There you go. No connections. That's the first case. If we have no connections, we're good. We can raise our own water level. However, if we do have a connection, how do we know we can begin filling our own thing up? Well, we use the idea of that barriered entry. Let's just, for now, the simple case, let's just say when we traverse down here, we have to have a water level of 0. So also the second case is if we have neighbors, if we have neighbors, but all of the water levels are lower than like we can't actually technically traverse, because let's say that the water would traverse if it was at 0.5. Technically, since this is 0.5, we should fill up this node to half and then spill over to here. That's how it should work. So that's the second case. Level, I'll just call this node water level is less than neighbor, which I'll call n. Oh, they're both the same thing. I'll just call it C. I'll just call it C for connection. And then C is water level. So that stands for connections water level. So basically, so n equals node, and C equals connection. So the data about their connection. There you go. That makes sense. So basically, the node's water level is less than the connection's water level. And this goes for all water levels. For all. So, for example, we can't begin to fill up our own water level if, for example, we had 3, and 3 we can traverse if we had 0 water level. All water levels would have to, like, basically be less than this. For all of them. All neighbors. That would be the second case. Then we know we can fill up our own node. Now, the third case is, okay, which we can kind of revert this back to, here. We don't need this third node to complicate things. There you go. Basically, what's going to happen if we can traverse this node and it's at 0? How do we know when can we start filling up our own node? Basically, when is this node, when has this node's water level matched the connection point? Oh, there you go. I just fucking explained it. So, we know we can increment our own water level. So we can increment the node water level if, for all nodes, oh, no, technically not. Yeah, that's the most simple case. The node's water level is equal to connections. I'll just call this connection level. I'll just say level. Which just basically means, so I'll also write this out where WL means water level. Actually I can type this out. I don't know why I'm not typing it out. Where WL is equal to water level. Here, expand this. L is equal to connection level, or just level. N is equal to node. And C is equal to connection. So connection level, water level, connection, there you go, that's your key. So for all nodes, for all, we know we can, if for all nodes, if their water level or their no, that's not how that's supposed to said. For all nodes where C's water level is equal to the CL, which I will actually change this. Instead of saying L, it's going to be, and then let me erase this. There you go. Erase it. Bam. Okay, so basically, CL is equal to connection level. And then that's an N. So basically what I'm saying here is for the node's water level is, or the node's connection level is equal to the C's water level for all of them. So in this case, basically what's happening is the node's connection level, which is basically the point they intersect at. So this would be the connection level, which is basically this, right? This is equal to the current water level we're at. So for example, the water level could be here, which is like 0.5, but once it reaches this, we know we can start adding into here. But that happens for all the nodes. Now, once that happens, we technically need to change the rate of flow happening, because we need to distribute this. Because once this happens, technically what is going to happen is more water is going to flow into here. It's going to flow in at a faster rate because less water is getting pumped into here. So it can't go anywhere. Because when the water level's down here, for example, for all these ones, this is taking some and this is taking some. But as soon as this happens, we need to kind of distribute what's happening. Which actually I don't think will be that complicated, because if I create a formula which basically explains, okay, which for example could be like, okay, we take the flow level, the rate of flow, and divide it by the number of sinks, or connections. There you go. So I could just remove a connection, apparently. There you go. So if I remove a connection, which means that this has reached like their matching point, the rate of flow will increase automatically. There's nothing complicated that needs to happen there. And then once, obviously, once there's no connections left, this can flow at a rate of 2. So once this reaches here, a rate of 2. However, how are we going to know when we should stop incrementing this one? Now, this is a new issue, and I think this is the last issue, hopefully, but, you know, you're typically wrong with that. Actually, before I go and explain that, because that's a whole issue in itself, let me explain the cases we found for when should we fill up a node. Number 1, and I guess I'll just type it out. Cases for filling up current node. What are the cases? Well, 1, you have no neighbors. No connections. I don't know why I can't spell it. You have no connections. The second is node's water level is less than the minimum, or like is less than the min connection level. That's a better way to say it. It's less than the min connection level. Now for 3, we can say nodes, all connections have reached the connection height between the node. So these are our 3 cases for when we can fill up a node. Basically means we have no connections, so we have no neighbors. The node's water level is less than the min connection level, which basically means, okay, we can't even fill up another node until we reach this minimum water value, which is explained like, which I can like draw edge cases for each one. Now 3 is all connections have reached the connection height between the node, which basically means that, for example here, this is filled up all the way and this is filled up all the way. Then we can begin to fill up the central node, because this has reached the max level it can get to, right up here, and this has reached the max level it can get up to up here. Then we can begin to fill up this node, which I can explain each edge case right here. So number 1 would be if we had a box like this. Number 2 would be if we had a box like this, where each box was actually higher up than the node itself. And then number 3 would be if would be like this example that we have from the start, which is this and then this. So each node has reached their like little connection point they technically have. So we're referencing this specifically. So the water level has to be here for this node, and then it has to be here for this node to start filling up. Then we can fill up. Those are the 3 edge cases I figured out so far. And here, this water level can increase up to this line, up to these points until it can like go up anymore. So it can go boom and go boom. And then this one honestly has no neighbors, so it can just go straight up. There you go. However, now we have the issue of, okay, technically we need to increment all these nodes. How are we gonna know now we know that this node itself can get filled up? How do we know we can fill up this node? Well, okay, let me try to simplify this by just doing the recursive approach. Well, here, this node will have a rate of flow of what? well, it have a rate of flow of these two different connections. Let's think about this. This node would have the case of one connection. It would just literally have one connection, which this no connections thing is really the rarest case ever. I would just assume if you just planted one rectangle. If you planted one rectangle, then this would it. So it's not even like the most common case. So this rectangle, for it to continue to fill up, it would need to reach the case 3. That all other connections, or its connection, it would have to reach case 3 because it's already filled up to here. One second. 3. For it to continue filling, it would need to have what? Well, it would need to match that. Technically, this water level is at 0, so it can continue going up because that's what it needs. Okay, so let me explain the issue I'm having right now. We have the simple case. These are all the cases for when we should fill up a node, but there's one more edge case I'm missing, which kind of might tie into just knowing the flow of water coming into a node. Because now, how are we going to know that we should continue to increase this one's value while also increasing this one's value, while also increasing this one's value, assuming that they've all reached the same water level? Well, let's actually just take the most simple approach to this one, this issue. Say we have one node. If we were to pump water into this, it would just fill up because it reaches test case 1, which doesn't have any connections. However, if we were to add this to the system, when can we fill up this node? When can we fill this up? Well, you can fill it up once the water level in this node has reached this point, which is edge case 3. Which is edge case 3, because it's its only connection and its water level has to be there. Which means we can actually begin to fill up this node with water. However, how are we going to know that we also can fill up this level too? Well, if I look at this node, which, okay, so if I do the rate where rate of flow is constant, which I'll call this RF, which is equal to 2. So this would have 2. This would go into here, and it would have 2, right? Because we're not changing it. There's no delay. There's no nothing. It would have 2. Because this is really simple. Well, how are we gonna know that we can fill up this water level? Well, if we look at this node, because each node will know what rate of flow it's gonna have, which basically for now would just be whatever rate of flow is in the system. So just one variable. We don't even need a store. Just one variable, because there's no nothing. We don't need to know how far away we are from a source node. We don't need to know nothing. That's too complicated for us right now. So technically, this would be a constant variable in the system. There would be no knowledge of, no node would know how much water is coming into it. We don't need to know that. We don't need to store that in the connection. Let's just keep it simple and get this working. So this node will know that it can fill itself up because it reached edge case 2, which is, okay, node's water level is less than the min connection, right? So this node can fill up because its water level would be lower than this, which is its only connection point. So then it's filling up, but then once it reaches here, it can still fill up because or no, it can't. It can't fill up because now you've reached the same water level. So now you've reached the same water level, which basically says, which removes the case 3, which means, or 2, 2. You have 2. Which removes case 2, right? Because case 2 basically means, okay, is our current water level less than all of our connections, like the minimum connection? Now, what's basically what we're saying is, okay, well, technically we would need to pump water into here. Water wouldn't flow that way or get pumped in there because it comes in from one square and it goes out, it spreads outward. But how are we gonna know that we can actually update it? Because we need to know that, like, okay, water would technically keep filling this up and it would begin to fill them up at the same time, right? How are we gonna represent that? How would we represent that? Because the problem is there's no case for, if we were to think about this one, this node, if we're looking at this node, there's no case to supplement that. You can't pass case 1, which has no connections. It does. It has a connection right here. Case 2 is water levels less than this. No, it's not. Water levels actually lined up with it. Case 3 is all connections have reached the connection height between the node. So it would actually use case 3 to be like, okay, I can blow up because my water level has matched with this. So then it would continue to fill. However, what would happen if we had a node right here? So, and then I can move this up. So let's move this connection point up. So so basically what would happen is it would use case 1, which I can I'll draw it out actually to make it more simple. The color would represent the case it's using to like move around. So using case 2, this node could fill up to this water level using case 2. Now, using case 2, this water level can fill up to here. However, the problem is this would reach first in the simulation. Because this would probably still be, if this is half, this would be here, up to case 2. Technically, this node would use case 2 to get all the way up, but at this level, at this point in time, which I'll represent with, which it would use case 2 to get all the way up to there. And then I'll represent all this with time t, which I'll just say 3 or something. It doesn't matter. There you go. You have this pink line. At this pink line, which is the current time we're at, it would be here. No escapes. I mean, I've heard of that. Cause I've seen this happen before, but I'm trying to derive this for myself, and I'm not gonna do it. I'm not going to use Google for it. I want to make it myself, and also that's for like, I'm more or less not worrying about the flow. Like, kind of like, this is really simple. This is simpler than that algorithm, because we're not technically worrying about any like direction. It's very, very, very simple. I mean, I bet you could use it for that, but I feel like this is simple enough where I wouldn't even have to use that his equations. So, but if I want to make this project way more complex, I would implement it with that. So, but for now, I want this to be really simple. So I'm doing it this way. It's a very particular reason why I'm doing it like this. And also I want to derive it myself. And currently I'm not smart enough to derive that equation from my head. So I don't even have the, I haven't even taken fucking differential equations or nothing. Or even physics yet, so. Okay, but back on this topic, we're at time 3, which means this is filled up to right here. And this would be at this water level. Technically, this would need to stop. This would need to stop filling up. Which it would, because it would break... well, actually, it wouldn't. It wouldn't stop. Because then it would begin to use case 3. It'd begin to use case 3 to continue to rise all the way up. Right, which basically means that case 3 is once the water level passes this point. Right, so every connection, right, that's what case 3 states. All connections have reached the connection height between the node. Yeah, because this is technically a connection, so look at this and be like, okay, I've reached it. This one has reached me because it's already connected, so it could use case 3 because this is already connected here. We have actually reached this one. Good, we can go up. However, we don't want that to happen because this water, all this rising would go and get dumped into here. Bitch, how do I want to solve this? Maybe I would have to change how I'm representing the connections. Because now with whatever I'm doing, this is it's not thinking. It's not thinking correctly. It's not smart enough. These base cases aren't smart enough. And then this water level wouldn't rise because this hasn't reached, at this current time, it hasn't reached the okay, so here's what I can do. I just thought about this, is for it to continue to rise, we can have the third case, which is the parent has to have all satisfied like nodes. Like all of this condition has to be satisfied. So when you look up, this whole thing needs to be satisfied. Which can be really annoying. But that's the solution that just went through my head is once we reach this and we break case 2, so I think case 3 is kind of bullshit. Case 3, shut the fuck up. Actually, case 3 is not bullshit because if it's this way, yeah. But it doesn't account for any future. If you go here, if you have an extra one, have that go up, and then you would stop. It's almost like what's happening is once this water level matches this, it becomes a part of this node. Like they become the same structure. Kind of. That's what effectively is happening. What do you say? Node 1, bottom 0, top 1, top 3, 3. What if you say node 1, bottom equals 0, top equals 1, node 2 is equal to bottom 0? Oh, so are you telling me to draw that map out? You say node 1, bottom equals 0, top equals 1. Node 2, bottom equals 0, 9, top equals 2. Node 3, bottom equals 0, 2, top equals 1, 8 or something. Don't know, I'm just thinking with you. I don't know. I'm also kind of confused with what you said. Like, no offense, like I'm a little confused. Do you mean like is that the rate of flow between those directions, or do you want me to like draw it out? Because this is like node 1, this is node 2, and this is node 3. I'm wondering are you talking about the direction? No, so you have a bottom and top every node. Oh, 1 second. Okay, so Phoenix, I'll answer your question. I've been coding for 4 years, and I'm currently in university for it. And I'm getting a computer science degree. If your goal is just to learn programming, I personally, right now, would say... Okay, so if your goal is just to learn programming, and you want to get a job in it, you need to weigh out the benefits of going to college. If you go to college and you struggle with math and physics, a big part of the computer science degree is literally math and physics. Because computer science is a generic field, and it's not just programming. So that's why they force you to learn all that stuff, because you're becoming a computer scientist, not just a programmer. Now, going to a school costs a lot of money. It results into learning some stuff that you probably won't know, depending on what type of programming job you want to get, if it's just programming. But there's a lot of benefits that come with university. Getting a degree makes finding a job a lot easier. Going to college gives you a lot of opportunities, like easier sort access to internships and career fairs, and you get to be around people who are also learning with you. It provides a lot of opportunity, but it does come back at the drawback of, learning stuff that you might not have to learn. A lot of time, 4 years, which is basically how long I've been programming, and I'm not 4 years into college. And it costs a lot of money, and it teaches you a lot of unnecessary stuff. But it does have a lot of benefits. Now, if your goal is to get a job, you would have to weigh between getting a job without having a boot camp, which, again, I don't really like boot camps too much, just from personal experience, because they cost a lot of money too, and they can kind of scam you. But if you're trying to get a job, you really need that credibility of saying you either went to a boot camp or kind of like a college. And also, if you go to a boot camps are falling out of favor in job seekers. It would be really hard for you to get self-taught, especially in this market, to get a job. I'm not saying it's impossible, but it would be super difficult to do that if that's your goal, which you can. But if your goal is to learn programming, honestly, if you were to even go to school or anything, you would learn programming from YouTube. You would learn it from YouTube, because the school is not going to teach you about programming like that. They teach you 2 languages. 2 or 3, and they just teach you math and all the other stuff, and they don't really teach you how to code. So if you want to learn how to program, definitely learn it from YouTube. And I would say, if you don't have the money or time, I would just try to go the self-taught route. And it's going to be a lot harder if your goal is to get a job, like a lot harder, but it's possible. So basically, to sum up everything I said, if you want to learn it from YouTube. Especially bro code. I really like bro code. Learn how to use a fundamental language like Java, or I personally recommend Java for beginners. They teach you the syntax of mostly other languages. Python's really simple to learn, but learn it from YouTube. I really like bro code. He's what actually got me into YouTube, programming. Like, he actually taught me successfully. And just build projects, and always be out there, always be asking questions, always be learning new things, and always look how you can improve yourself. I'm a freshman, and I'm a CS major. I'm being taught C. I'd say the courses course is math intensive, but it's very worth if you're looking into AI/ML. Learning C is not bad because it's lower level. Yeah. Exactly. At my university, they only teach you C, Java, and Python for one class though, but they teach you a shit ton of math, which for a lot of people who maybe just want to build, like do websites, or they don't really want to go into math intensive stuff, because a lot of that stuff is already abstracted away for you. Other people will do it for you, and your job probably won't require it. It's not really worth it. And learning C is really good. I would say learning C is like really is good. Everyone should do it, especially when you learn how to program, because it teaches you how the computer works. But the problem is it's kind of hard to build cool projects that could keep beginners interested, and it's not very like applicable for like what a lot of people want to do. Like a lot of people do want to build like back-end systems or front end and stuff like that, which C kind of sucks at doing. Yeah, dude. Yeah, Phoenix. If you want to do AI/ML, definitely you should probably go to school. Because they will help you with that. My math professor currently does a lot of machine learning stuff, and he always relates back how in Calculus 3 how all the top like the concepts work with machine learning. Okay, if you're still here, I don't know how to say your name. Faith. I might be stupid. No, okay, but let me go back to what you were talking about. No, so you'd have a bottom and top every node. A bottom and top every node. You know, I might be really stupid, but I still don't understand fully. Yeah, I'm minoring in math for the exact same reason, because like I only need a couple more classes, but I'm really minoring in math because like, yeah, I only need a couple more classes, but I also want to like apply my math skills. I actually want to like go into positions where I know where I can use math. I do think math's cool. Yes, you have also stated the breaking points, like node 1 when it reaches 0. Oh yeah, 8 and node 3 reaches 0.5. It needs to also flow in node 1 and 2 and 3, but after you reach the top of node 1, you don't need to fill it. Yes. Oh, okay. Yes, you also stated breaking points. It reaches 8. Oh, I see what you're saying. Oh, your commas messed me up. I thought 0.8. You're saying 0.8, not 0.8. Yes, you must state that breaking points like node 1 when it reaches 0.8 and node 3 when it reaches 0.5. And node 3, it needs to flow also. It needs to also flow in node 1, 2 and 3, but after you reach the top of node 1, you don't need to fill it. Okay. Well, yeah, okay, so once we get to this point, I was thinking about like a solution, which this was kind of like I was talking about earlier. I got distracted by talking to chat to you guys when I was talking about it, the solution. But basically what I was saying was we could add another case, which basically the first case, this uses case 2 to get up all the way to this point, which is it only has one connection. 3 only has one connection, which I'll draw it out like this. It connects to node 1, right? But it needs to be up at 0.5 to flow into node 1, right? Now, once it reaches this point, what case can we use to be like, okay, well, we should still continue to flow this up? Well, the issue is we can't flow this up until this node is satisfied until we can't wait. Okay, so we can't fill this node up. We can't fill up node 3 until this connection basically has all of its other conditions satisfied, which basically means we can't fill up a node 3 until node 1, or oh, this is node 2, my bad. No, until node 2, which, you know, connects here and then it connects to node 1, right? They all connect back to each other. If we're at 3, which is with this one, right? Node 3 is filled up to as much as it can get to. Now we can't fill this node up anymore until node 2 has satisfied that case 3. Once node 2 has case 3 satisfied, which basically means, okay, I have all this finished, I have this connection finished, I have this connection finished, then we can begin to flow. So once node 2 passes case 3, we can begin to increment this again. Once this is the case, we can begin to you know, start increasing ourselves again. And then again, for anyone that doesn't remember, case 3 is all the connections have reached the connection height between the nodes. So basically, when it would look like this, for example. So we can begin filling up this node if all these connections have basically filled up to as much as they can. Now that would only happen. Now here's like what's something that I'm kind of realizing. This case would only happen if these nodes down here, they also have filled up their children, basically. Ooh, what the hell? All the way up. Because unless they haven't filled all the way up, they can't reach case 3. They can't. They just can't. Which would mean that... But that kind of goes off the parent architecture, because what if we had, like... Oh, see, because what if we had another container right here that went up right here? Well, technically, okay, well, this would be node 4. Well, node 4, we can't fill this up. Oh, well, this doesn't matter because we can't, there's no rate of flow coming in here. We can't flow this up. We can't fill this up until it reaches 0.6 or whatever it's at. So this rate of flow, this barrier to entry doesn't even affect this logic that I'm thinking about. So basically, we can tell if something's a parent if our water level matches the connection line, which for here would be 0.5. So if we're at 0.5, we can look and we can be like, okay, I see this. This is technically the parent, whatever. This is our new dependence. And then if this dependence is like, okay, well, all my children, which is 1 away, it would just be 1 level away. That would be the children, right? It would be 1 level away, and 1 level away in this graph would be 1 and 2 from this one, or 1 and 3. This node, that's 1 deep away. If it knows that, okay, this condition satisfied, this condition satisfied, they're all at the correct level, I can begin to increment myself. Which means this is incrementable, this is incrementable, and this is incrementable. Yeah, but I'm kind of confusing myself because there's so many moving parts happening right here. I need I think I need to rethink this. First of all, how are we going to even iterate over this graph? Well, we have a source coming in. And I think what we can do is we can just follow the source of water. Because the only way to solve this issue kind of right now is if I actually think about how we're going to traverse this graph, how are we going to increment the water levels? How are we going to know when we should do that? Well, technically what I said was right now we'll have a base water level, which is inherited by all of the nodes. Right, we're not going to worry about knowing how much water is coming into a node or like doing the effect of dimming it out, because that's kind of complicated. Let's just think about this. We know every node should fill up at the rate of 1. We're basically just checking each node and seeing if they can fill up. It's basically what we're doing. So if that's what we're doing, if we're just looking through each node every single time and we're checking, can we fill this node up, or can we fill up other nodes, right? That actually makes this problem a lot more simpler, because now we can look at each node individually and just break them down into the 3 components. So for a simple case, it's yellow. For a simple case which is all nodes have the same flow rate. Alright, this is the most simple case. This is the easiest way to prototype this. Here's what we're gonna do. Damn, 2 hours. 2 hours just playing this out. Insane. Okay, so when they all have the same flow rate, all the program is doing is checking each node to see if it can fill up. Right? That's all we're doing. That's all the program's doing. Well, what's the first case it can fill up? Well, it has no connections. What we said. The second case it can fill up is if its water level is less than the min connection level of all its connections, right? Which basically means its water level is less than all of its minimum connections. The third case would be all of its connections, or the min connection level, or the next connection level, the next well, because if you have a connection, I don't want 0 point the parent to the tick to determine that. 6. How can we handle this? So no connections or water level is less than the min connection level. If that's the case, 4. Well, 4, I would only want to do that. Fill that up. That would get filled up to 3. Then you would move to 3. Because the way I'm looking at this, so if 4 wanted to fill up, we have a connection, obviously. And then, obviously, we're going to fail case 2, which is this. So that means the rate of flow needs to go to here. Which then we check 3. And then 3 can pass up to level 2. And then once we pass level 2, we can, where is my, like, movie thing? Once we pass, so if we made this the source, what would happen is, this would fail all the cases, because it doesn't have any connections, and its water level is actually greater than the min connection level, which the min connection level is 0. So water would go down. Water would then begin to fill up here because it does have a connection, which is 4 and 2. But the min water level of the min connection is 0.5. Okay. So this rate of flow would go into here, and this would begin to fill up all the way. Now, once this happens, how are we going to know when should, because we can't fill this up anymore. If we look at 2, well, 2 can't fill this one up anymore. Because I want to follow the rate, I want to follow from the source node. Because if I just kind of be like, okay, well, every node fills up at 1, that kind of defeats the purpose of giving it a source node and, like, simulating how a container could fill up given a source node. Right? Which defeats the whole point of the whole, like, system. Well, how can we, like, see it? Well, this would actually transfer, this rate of flow would actually transfer to here, to 3. So technically, we're pumping 1 rate of flow into here, and then this, for every iteration, is not getting this water to flow anywhere. Well, once it reaches this level, which is this connection level, it should flow, this should keep getting flowed in, and then it should, like, kind of spill out to here. So this should start filling up with 1. Now we look at 2. So every iteration we go 4. Okay, we can't. Okay, 3. We have an incoming connection of 1. So we can raise this up, but we can't raise it anymore because we're at a certain water level. So we have to spill over. Oh, wait. So 2, once it hits this, it knows that it needs to spill its connection over to here, 0.5. It knows it needs to go over to this one. It needs to transfer its water flow to here. Now it transfers it to here. We're at 2. 2 then looks at its current connections, which is 0, 0, which is 1 right here and 1 right here. It knows that, okay, we've already, which, again, we don't want to circle, because this is gonna, because if I say, okay, we look here, this is gonna circle. We don't want it to circle. Maybe we do want it to circle. I don't know. Whatever, we'll just say for now, if their water level matches up with this one, don't go to it, don't flow over there. So we flow to the lowest one, which is how much remaining it has to go, which would then be this one, because this one still has to keep coming up. Once this is filled, and technically this is zeroed out, this is zeroed out. Which basically, if we had a variable, what I'm saying here is basically if we had a variable which tracked how far away, what color can I use? How far away it is from completing, like lining up. Which would basically be the node's connection level. What did I say for this? It was the node's connection level, whatever. As long as this water, the connection water level is equal to, or water level minus the connection, or the node's connection level. I don't know. I forgot what I named that shit. I'm actually gonna delete that. That's confusing. Yes, Paul. Yes, we're almost done though. We're almost done. It was. We're currently solving the issue of. We know now how we transfer the rate of flow, but now we need to figure out what's gonna happen if these nodes fill up at the same time. Because now technically what's supposed to happen is this is supposed to fill up, this is supposed to fill up, and this is supposed to fill up all at the same time. Which I don't know if I'm overcomplicating this or what's happening. I think I'm overcomplicating it for sure. But we have planned out everything to how to disperse, which should technically go first, and all that stuff. Now it's just the issue of tackling, okay, once everything's at a certain level, how do we raise that water level at the same time for all these nodes? Which I don't understand why I'm having such an issue with that. So we say that this is 0.5. This rises up, which we can't, so we go to node 2 because it goes to the next one. It goes to node 2. And then node 2 technically should fill up. But node 2 can't fill up because it has to go here. Because use a monotonic stack. And she right. The upper dimension could be negated for now. Use a monotonic stack. Okay, so well, when I use a monotonic stack, what do you want me to be storing, and what should be the condition for popping and pushing? Because I know about monotonic stacks, but monotonic stacks are one of my worst. I always like understand the use of a monotonic stack, but anytime they give me a problem and I gotta fucking look at it, bro, I will never figure out a monotonic stack solution. I do not have an ability to derive a monotonic stack solution. But you might be right. Okay, so 4, 0. was 0, so you go to 3. With 3 you got 0.5. And you go to 2. Okay, well 2 technically, if you just, okay, if you look at your connection, which is 0.5, or not your connection, you can't fill up until what? You can't fill up because of case 2, which basically says you have to go down here because your water level is equal to this, so you gotta go down here, and you gotta technically technically you have to go back down here, but you don't because this has reached your current connection level. So that basically means don't actually take this path. Don't take this path if the water level matches up with its connection level, right? Don't take this path if this happens. Take this path because this is not matched up. But once this matches up, and this matches up, you can increment it. You go down here. How do we know we can increment this stuff? Okay. Thinking. Red flow 1. Okay, you... Bro, this is the last thing I need to solve. Once we get this done, we can finally start coding. I think I'd have everything figured out. I don't know why I'm complicating this so much. Alright. Reset. We have here. This fills up because it has no connections. Okay. This would then, if we make this the source node, this would attempt to fill up, but it can't because it has to take the path of least resistance, which would then take this one. So then this would fill up. This has no neighbors, so it passed case 1, which would fill it up all the way to here. And I would just assume every iteration we would just follow the path of the water. So we get to here. Now on the next iteration we go here. How do we know that we shouldn't take this path? Well, technically, if this water level is the case, and this is the case for all neighbors, if they match up, or if it's matched up or it's greater than, just increase this water level and increase your water level. And then don't go any further. Alright, I figured it out. Let me explain what happened. Wait, did I? Yes, I did. I think I did. I think I finally fucking figured it out. It's been 2 hours and 30 minutes. I've been playing this the entire time. This is crazy. Technically, I've only been planning for 2 hours because I spent 30 minutes explaining the project idea. Okay, so cut me some slack, but I think I figured it out. This is node 1 for everyone's information, and this is node 2. Now, what do we store by? And remember, these are a graph. This is a graph. This connects to here, and they connect back. It's bidirectional, right, guys? Remember that. Now, we can mark one of these nodes as a source node. Source node means it outputs water, right? So this, which we'll mark in blue, is the source node, which I'll just color in blue a little bit. So technically what's happened here is there's a flow of water, any direction, it doesn't matter, but we'll just say there's a random flow of water coming in, and it's coming at a rate of 2. For now, to keep everything simple, we won't need to worry about, or I said 2 and I wrote a 1. It's coming in a rate of flow at 2. And we don't need to worry about anything else besides that this water is coming in at a rate of 2 from this source node. Now, we're currently, when we iterate through the program, we're always going to start at the source node and just run through the entire program. How about that? That's the simplest way to handle this. the simplest way to look at everything. We're just gonna start at the source node and loop, like just fucking travel along the path. Now, the flow of water technically. Oh, one second. I know I was explaining really well. One second. I need to handle something. Alright. Let me leave off what I was talking about. Alright, next working. Alright, so basically what's gonna happen is we can mark any of these as a source node, and we will right now this is not the most optimal solution, but I don't care. So what's gonna happen is we get a rate of 2 coming in, just for example, and we are gonna visit this node first, so we start at the source node. Now we're gonna check. Can we fill up this node? Is this node going to be able to get filled up? And we can see that no, it can't. Why? Because we have this connection point. So, since we're traveling along this path, we need to travel. This will cost us 0. Which basically means to take this path, we need to have 0. Which, again, is the minimum. Technically, our water level is equal to the minimum connection level. So, we need to take that one. So we see that right here, to get to 2, we have to have a water level of 0. So because that is the case, we are going to travel to this node. Now, we can see that in 2, what's going to happen is, and this is traveling with a flow rate of 2. Basically what's happening is because right now we're not dimming the effect, it's just getting sent over 2 water sources. So 2 water sources are now getting flown into here. Now for 2, can we fill this up? Well, first of all, it has no neighbors, and its water level is less than the minimum connection point. So for 2, this connection point is again right here, and this would be at it would be this like orange part, which is the circle, right? And this would probably be at 0.6. For simple, obviously it's not to scale, but we'll just say 0.5 because it's super simple. Its water level has to be 0.5 to travel. So for this node, for the water to go anywhere else, if we look at the simulation, we start here. We see where can the water go? Okay, it can go here. It can go here. So we pass the water over to here. Okay, we're here now. Where can the water go? The water can't go anywhere. Why? Because this node's water level is not. It doesn't have enough. You can think about it as cost. It can't pay for this toll fee. It can't afford to take that thing. It's too expensive. So it has no neighbors. It can't go anywhere, which is our 2 cases. So obviously we can increment it. So if we increment it, it would fill up. We start back at the source node. Follow this down. Okay, yep, there you go. You can't go. Okay, yep, follow it down. Yep, there you go. And then it does that until it reaches up to this point. Now we're here. So again, we would see that it's here, but now we have the unique case where it's cycling now. Now it's cycling because what's happening is it's going to. Okay, well now we can ensure it's here. So basically, if I draw this path, if we start here, it's gonna go here because water has to go to the lowest cost. Now at this point, this is 0.5. It's gonna go and circle back. And now since it's circled back, we know that we're in a cycle. We know we're in a cycle, and obviously we can use an algorithm to detect if we're in a cycle and all that happy stuff. But this node is in a cycle. So at this point, we're in a cycle. Which, once we detect this cycle, we know we can just keep incrementing these values. So now we know that, okay, this node's in a cycle. So anytime we travel along this cycle, we can just increment the node, increment the node, increment the node, increment the node, and increment their water level. Because imagine if you had, like for example, you had, actually I won't, I'll keep this simple. So now that we're in the cycle, we know anytime we travel along the cycle, we can just increment the node's water level. So once we detect that, we're like, okay, so increment this, increment this, increment this, and then you keep doing that. However, once a node reaches a water level of 1, meaning it's completely filled, or, what was the case that we said? Whoa. Didn't we say we couldn't have air pockets in this simulation? I think I did. I think I said that there was no such thing as an air pocket in this simulation unless you made this the source node. So the simulation will continue until this node equals, until the source node equals 1. So as you travel along this path, we'll increment this. So this will get incremented, then this will get incremented, and then once this reaches full, you can't traverse this node anymore. And the cycle will basically break. So I think basically the solution for this was to travel along the node, and then just increment as you go. I think that literally was the solution. What? Yeah, I deadass think that was the solution. Because air pockets can't exist, so air pockets can't break it. I mean, if air pockets were a thing, all we'd have to do is just store this top value. Where is my master? If that was a thing, you could just do that. So I think literally the solution this entire time was just to follow the tree with those 2 base cases, which is if it has no neighbor, or if it has a minimum water level. That was literally it. Wow. I think that works. So basically, the solution is you start at your source node, you travel along until you can't go anywhere, you increment that until you can go somewhere, and you just repeat that process. And if a node is completely filled, then you don't go to that node anymore. Why that works is because for a node to be completely filled, all its neighbors, or all its like neighbors that can like impact it directly, have to be filled itself. So, because 1 can't fill itself until its nearby children that are like at least below it are filled, and then you continue the simulation until your source node completely fills up. Because once your source block fills up, then you can't put water anymore anywhere else. Because water can't flow directly up here unless you like force water to go through the thing, but we're not assuming that. So let me storm up a couple of cases real quick to prove that's how this works. So the first case would be this. So you have 1, 2, 3. For us, we can assume that every connection point is at 0.5, at least this way. Or, well, yeah, so this would be 0, this is 0.5, this is 0.5. So if you go down here, that's 0, traverse up, you get this. And then you would get this graph. You get 1, which goes to 2, or 1, which is connected to 2, which is connected to 3. Now, let's make, for the simplest case, let's make 1 our source node. And then obviously, so we follow this, so we take the 0, 0, 0, this is 0.5, 0.5. There you go. So we make this our source node. We go down, we take this one. Okay, we're at 2. Okay, we still have somewhere to go, right? Because of our 2 conditions. Our 2 conditions to fill up a node is you have no neighbors, or your water level is less than the minimum neighbor value. So if we go down here, we're at 2. Okay, we have to go this way. So we go to here. Now, this water can't traverse this way, right? It can't traverse back up because it needs 0.5. So it begins to fill up then. So now every time you run this, this starts to fill up, which would fill up to around right here. I know this doesn't look like 0.5, but just imagine. Now that we're at 0.5, what's going to happen is we traverse. I'll rewrite this. Now that this is at 0.5, what's going to happen is we're going to go right here. We're going to go right here. And now we can actually take this route. Now we're going up the chain. Now, can this node keep going up? No, it can't. Why? Because this water level is at 0 still, and it can't go up. So then we begin to fill this one up. But we also have to make sure that we're gonna fill this one up too while we're doing that. So how can we ensure that we're filling up both? Maybe I could just say, oof, god damn it, again. Now we know that, like, since this is at 0.5, we can go back up to here, basically traveling up the chain again. But how do we know that we can begin incrementing this? Which I thought I just solved. Go down, you go down. Jesus, bro, my brain's like shitting the bed right now. So bad. I've been at this for fucking almost 3 hours. Started to take a toll on me. Starting to get me mad. I just solved this issue. Okay, well, I mean, technically what's happening is you flow water here, you flow water here, and this one is like, okay, I can't go anywhere, so you flow water here, and then you flow water here, but then you check, okay, well, 0 lines up with this, so you technically flow the water into here, and then you get a cycle. Node top, WL. Node top water level. Yeah, you're right. So, okay, I guess what we can say is we can increment this one while also flowing to this one if the node above it, water level, is so this is basically saying we can traverse here, right? Which means we can flood here at our current water level, which means we need to flood here, and then we, you know, get into this pattern. But if this node's water level is equal to what? What can we say? What do you think we can say to say node top's water level is what? What is it equal to? Or what is it less than? Or what is it greater than? So you would have something to stop filling the water of it reaches top water level. Oh, top water level. Yeah. Okay, well, what would the top water level of node 3 be? 0.5? Because if we have, like, here, this one, the lowest one would be 0, right? But we have it, so we have 0.5, which is the top. Once it reaches the top water level, but we would still want, but wouldn't we still want it to be, we would still want it to be filling if it reaches the top water level, or am I not talking about the same thing you're talking about? Is this what you mean by top water level, which is this connection point that they have? Because here's my issue right now. The problem is like, since we're doing a graph, like, this graph can have multiple children, and they can all be connected, right, in some weird format. So saving the state is weird, which I think gets solved if we make it directional. Wait, instead of like traveling, no, because then I want the spill. So no, it would need to travel both directions. Right now, it'd go here, it'd go here. Once it reaches this, which is its top water level, we would need to transfer. But again, the conditions state, the two conditions we have, which is no neighbor and you have a second condition point with node 2. You have a second connection. Oh, you have a second connection point with node 2 and node 3, which is the top water level of node 3. So right here, which would be for node 2, like we'll just say 0.3. Okay, I see what you're saying. I see what you're saying. Okay, so we have that, which then we'd have to store one up here, right? Go up. Source, go here, go here. Go here. Wait, that doesn't make sense. Never mind. This doesn't make sense because this is supposed to scale. My bad. This almost fucked me because this is supposed to scale. Technically, this connection point's at 0.5. Let me actually move that so it makes sense. Because this connection point's supposed to be at 0.5. This is supposed to be half of the tank. So I mean, the top of the connection point would be, wouldn't it be? Well, for us, it would be, you could just take the opposite thing and then minus it by 1, and that would give you the top of it. Okay, well, okay, so what we could say, like, a simple case is, okay, if, oh, how can I, you're filling up this, you fill up this, right? This gets to this connection point, which is, for itself, 0.5, which means it can flow into here. And then you have, then we need to see if node 2 can fill up. Node 2 can fill up here because node 3 is equal to its connection point. That's what you can say. Say node 2 can fill up because its child, which is 3, is at the same, like, water level of its connection point, which means you can increment 2, but it also means you have to increment 3 because we haven't reached the top of 3. Remember, we said we would stop searching the graph if a node became completely filled. So if a node became completely filled, you'd return out of the graph. You wouldn't keep going through it. Right, so through this case, what would happen is, okay, we see that node 2 can fill up because node 3, right? Node 3 has reached its connection points, reached the same level. There's like kind of like a level right here. So now this can continue, and since node 3 isn't also like filled, we can actually traverse to this one, and we can see that okay, its connections have reached. We can increment itself. So let's say if water reaches first connection water level of node 3, start filling node 2 and 3 until reaching top level of node 3, then start filling node 2 until, say if water reaches first connection water level of node 3, which means it reaches this, right? Start filling node 2 and 3, so fill both while this is the case, until reaching top connection level of node 3. Oh no, you're good, you're good. Oh, I see what you're saying. Okay, okay. Good. I like that. I like that train of thought. Okay, what happens if I Jeez, this is taking so long. It takes so much longer than I thought it would. I didn't realize how stupid this is gonna be. Okay, but here's the problem. What if I have a What if I have oh, this won't matter because the way that I have it set up is there's no like above point. Well, if the above point matches directly up with this, okay, what would happen if I have like something like this? So like they connect at 0.5, which this would be node 4. So for node 4, what would happen is water would come down here. We would check this condition. Do we have any connections? No. Or we do. Are those water levels matched? No. Is our current position less than, is our current water level, like, can we actually go there? Yes, we can. Okay, so we traverse. Okay, can we actually go here? Yeah, we can. We can go to 3. Okay, so we can go to 3. However, again, what needs to happen is, say like this is the case. Say that they're all at the same level. They're all at like 0.5 of connection points. So we know we need to fill up 2 and 3 from earlier. If node 4 didn't exist, we know we need to fill up 2 and 3 because node 3 has reached like they have met the same level, right? So we know that we can keep incrementing each other. However, what's gonna happen with this node? Well, if we traverse the 3, can we fill it up? Yes, because it has reached the, or technically, well, that means we can fill up 2 and 3. So we can go down to here. Start filling node 2. If, let's say if water reaches current water connection water level of node 3. Start filling node 2 and 3. Here you go, 3. Okay, so again, we would have a cycle. Maybe, okay, one second. One thing I'm thinking about is like using this cycle to our advantage. Like, I generally think that this cycle could actually play massive roles in this success. But I think I figured it out. How we can use this cycle. 1 can go to 2. Alright, this current rate, 1 can go to 2. 2 can go to 3, and then 3 would stop. You'd have to fill up 3 to a certain point. Once 3 gets to that point, oh, also 3 has 2 connections, so we would 3 technically would be connected to 2, and it's connected to 3, and this is only connected back. So 3 does have 2 connections back. It's this and this. So you'd have a 0.5, and then you'd have 0.5. This would be 0. Like I said, to get the YouTubers, each register cost of 0 here, your credit register cost of 0. If you start here, this is your source. Okay, you go, boom, boom. 1 to 2. Again, you don't traverse because you go to lowest cost, which this is 0.5. So you go to lowest cost. So you go to 3. Now 3 is at 0.5. Since 3 is at 0.5, because that's how it would fill up. It would fill up this one first. Then 3 has the ability to go to 2 and 4. And then how would we detect a cycle here? Because wait, can fast pointer detect cycle in a graph or only linked list? Can fast slow pointer detect cycle and graph? Or is it only in linked list? Do we know? Does anyone know? I mean, we just BFS it. We can BFS the search, but technically, goodness. Oh my goodness. This is becoming silly at this point. Okay, so we have this case, which means we need to fill up 2 and 4 at the same time. However, okay, so here's the issue with what I'm having here. Okay, so maybe I can add another condition. We can check the current water level at this node, which for this is 0. This current water level is 0 too. Now, for example, we can say... What can we say so it fills up in the correct order? Because this current water level will be at 0. 2's water level will be at 0. Can you draw a line from left to right with different colors for every... Yeah. So currently, this is what's happening. Let me go back and draw this again. Okay. So the initial here, I won't even do it in the graph. The initial goes here, goes into this, and this will pool up into here. Now what's gonna happen is this needs to go somewhere, because this has filled up to its max point, right? But it can go to these 2 different places. So obviously what we need to do is we need to fill up 2 and 4. We can see that. But, I mean, obviously if we had a... The problem is we can't fill up this spot until they match. They all match. Same water level. Which actually, I'm assuming if... What am I assuming here? Let me like draw some here. I know I'm making it really complicated, so it's like getting hard to even like explain this. Oh my goodness. Okay, so this would fill up in the first like actual like, iteration of everything. Now this water can go to 2 different directions. It can go to 2 and it can go to 4. Well, if it goes to 2, it obviously 2 knows that it can fill up. But how does 2 know it can fill up? But the problem is, because if we need to go to 4. So we go to 4, the water needs to flow down to here. And then this will fill up all the way up here. And then we have this issue where we basically need to know that, okay, all these are at the same level, which means we can increment it. That's the issue. Once we figure this out, incrementing it is not a problem. Like, actually solving this is not a problem. But it's traversing it, which is the problem. Okay, so now we get here, because it would theoretically take this path. Now this is coming out. So it would have to come out and then fill everything else. While also filling itself, but that's not the issue. Now the way I was gonna solve this was because we need to traverse this via a graph. Maybe there's a way simpler way to do this, but right now I think it's a graph. And we do 1, which 1 connects to 2, which 2 connects to 3, which connects to 4, which connects to 5, right? Which is, it's just like a long linked list, basically. The way the water will traverse is it'll start here, it'll go down to here, it'll go down to here until this reaches 0.5. Once this reaches 0.5, it can go 2 different directions. It can go here, which I'll draw as an orange. It can go here, or it can go here. If the water takes this path, it will go here. Water will never rise until a node is filled until hitting the connection water level. And then CWL means connection water level, right? Just make sure. I know I made up that terminology, but I'm just making sure that that's what you mean. You think you think it might be simpler if I... So what's happening here is I'm like thinking about this flow, and then like, you think it would be simpler if what I did... Okay, so water level will never rise until a node is filled. Until hitting the connection water level. Okay, well once it hits this connection water level, my question is it goes here. And it hits this connection water level and all this. Hits all of this. These two. It meets these 2 conditions. So it should go fill up 4 and 2. But 4 and 2 can't fill up because they depend on 5. But we know that 4 can't fill up because this connection isn't met, right? We know that 4 can't fill up until this connection level is met. But the problem I'm having is 2 doesn't know that 4 depends on that. Okay. So in this case, you will first start filling node 3 till current water level, which is node 5. Then it will go to node 5. Fill up this. Okay, so it will go down here, go out here, fill up node 3, right? Then it would go to node 5. And then it would attempt to fill up node 5. Then 4 is satisfied. Yeah, but my issue is how are we going to tell the program to do that? Like, are we still all on board on using a graph, or is there some other data structure we can use? I know some other guy came in here and said monotonic stack, but again, I cannot figure out monotonic stacks to save my life. I mean, this is the last edge case, by the way. I'm pretty sure this is the last edge case, because if they're all at the same level, then you need to know how to update all the nodes. But besides that, like, this is it. Well, okay, so when node 5 reaches its top, it'll go down, it'll reach node 5, and then it will start to come out. So it'll come out, which means, okay, I can fill node 4. Because node 5 just reached its happy place. But, oh, you know what we could do is we could store the depth. We could store the depth away from the, Hey, well, you're giving some really good advice for being a beginner, I'm not gonna lie. Come up with some good things. Okay, so here's something I just thought of, is what we could do is we could store the depth away from the starting point. So we do 0, this would be node 1, this would be 2, this would be 3, and this has a depth of 4. So when we hit 3, basically what needs to happen is we need to go deeper down the graph. So we can basically look, and they will share the same like current water level. But we'll know, just pick node 4, because node 4 is farther away from the source node, which means that we're not in a cycle yet. So we'll pick this one because it has a farther away from the source node. So we'll pick 4. We see that 4 has another dependency. Then we go to 5. Yeah, maybe. Okay, so here's why I'm thinking we don't have to do that, is because if we can get like a path correct, what will happen is if a node fills up all the way, right? So currently the water is taking this path, right? It's going along this route. So it'll go here, and then it'll go up, and then it'll go down here. The thing is why I'm thinking we don't have to store at the top water level is because what happens is once this node fills up to full, this is like the current state of all the other nodes. Well, here, actually, this node will fill up first. So number 5 will fill up all the way, and this is what the current state of the map would look like. Once 5 is saved, it's fully fat, it will turn 1, which means it's fully full, and we can't follow a full node, right? So we would never traverse this path again. So currently, after this is filled up and we take this down, we would go to 2, we would go visit 3, we'd go to 4, but then we wouldn't go to 5 because 5 is taken. And this is the path we would take. Then this would begin to fill up. And then after 3 fills up, this is what everything would look like. It would look like this, right? Now, once 3 is filled up, the path would look like this in pink. It would go down here, and once it sees 3, which is full, it won't continue to go, because you can't push through a full node. So then it would just go and dump into here. And then once this is all filled up, the state would look like this, and then it knows that it can't go anywhere, and it would just fill up this all the way to the top. Well, okay, are you saying, like, the part we haven't figured out is basically what's gonna happen if they're all at the same, like, level? If we have multiple nodes at the same level, how are we gonna know how to fill all of these up at, like, the same time? Basically, is what we're trying to figure out. Because we have 3, which is here and here. Okay, so we know, but so 2 thinks it could fill up because 3 satisfied, but it doesn't know that 3 also is dependent on 4, which is dependent on 5. Which, so that means 5 has to fill up, and they would all need to fill up like that. Also, what I was saying, okay, so, and also to answer your question is, are you saying, like, this is a logic error, or, like, in real life, if we were to pump water into this system right here, we were to pump water into these tanks, 4 would still fill up anyways, even if 3 is full? Um, I, I discussed at the beginning of the stream. I thought it did. I don't know actually for sure either. I thought it did, but then I was like, wait, well, how do air pockets work? So I said it didn't. Because how do air pockets form if that behavior isn't true? Oh yeah, you're right. 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 Wait, if that's the case, then I think this actually makes it so much simpler. Because you know what we can do if that's the case? Oh my god, don't tell me that my own dumbassness, where I thought that that's how air pockets worked, just made this so complicated. Because wait, if that's how that works, then technically, wouldn't we just go down here? We would go down to here. If this is empty, we would fill this up. Once this is full, we would just keep traversing, right? I would want to keep traversing in this direction, at least to the next like lowest one that we have access to. So we would find the next like lowest one, which would be, so we would like collect the lowest water levels out of all these ones, find this one, and then we would go down here. We'd see that we have no lowest one, so we just begin to fill this one, fill, go down to here. Then we can, okay, right. Because I was also thinking at the start, I was like, wait a minute, that doesn't make sense, because if I'm pumping water into a system, like, it would force the water molecules to go up and fill like the tanks, even if there's like, even if like there's stuff like this. Okay. The fuck is this shit? Yeah, you're actually right. Yeah, honestly, maybe you're right. Maybe I should just begin to like code at least like the basic parts, and then we can see it in action. So I've spent 3 hours sitting here doing jack shit. Three, 1, 3, 2. Alright, I think I have a decent enough solution. Okay, before I start coding, we have the ideas, we have what we need, we're going to traverse like a graph. We're going to do a BFS, but we're going to search basically. When we go down here, we just go to whatever has the lowest water level. And we'll just follow the path of water. What gets queued, how it gets queued is it'll get sorted based off the water level, and it'll pick, it'll try to follow the one with the deepest depth path. But if it has, and the depth path basically means how far it is away from the source node. So since this is the source node, it'd be 0, this one would be 1, this one would be 2, this one would be 3, and this one would be 4. So if they share a water level, we'll originally sort it based off the water level. If that's not the case, then we'll do it based off the depth level. If the depth level is the same, it doesn't matter, and we'll just keep doing it. I think that's the correct way to approach this. So, I haven't wrote anything, so it's gonna be good. Let's just print out a nice little hello world. Let's make sure that everything's building. There you go. We're good to go. Alright, so the first thing we're going to do is we're going to define what a node is. Which, for our cases, should make it a class. Node. And we'll give it, you make a constructor, oh, it's a net, right? And you make a constructor in Python again. I don't really code classes in Python a lot of the time. init, yes. Go. Currently, we need the self. We need the. What do we need out of it? We don't. I guess we can say we could pass in an array of neighbors, I guess. Just call that. I'll just call it connections, like how we did in here. Connections. Pawns for connections. There you go. Connections. Connections. Thank you. Again, you don't do that up here. And I'll say self.connections is equal to connections. There you go. And what else do we need? We can say self.waterLevel. Or water level. Oh, it's snake case in Python is equal to 0. What else do we want to store? Yeah, I think that's all we need to store for now. And then we can make our we can make like a simple graph, so we can say mat or graph is equal to, and then let's just make a simple one, which is just going to be a node which has no connections. How do you do? Oh, it's not in Python. It's no connections. And then find PFS, which takes in a node. Or I'll just call it a node. We'll make the cube which is equal to collections. What's the how do you import a queue in a queue in Python? Python queue. It is queue.queue. I don't have any ports queue from queue. Oh, I did not like how I said that. Oh, do I even have to import anything? Oh, it's from collections import deck. And then down here it's a deck, which I'll call it a deck. Then we'll append the node in the queue. Keep a set, which basically set a visit, which is a set for any cycles. While queue, while length of queue, or while queue dot length. I can just say while queue, I'm pretty sure, right? I don't have to say let's say while length of queue, because I don't think queue will return null when it's empty. While queue exists, basically cur is equal to queue dot get, or what is it? What is it in this? Queue dot pop left. Pop left. If cur if cur is if not or if geez, cur in viz. Okay, continue. Else, what we want to do is we want to say viz dot add cur. Go. Now for n or c in cur dot connections, if cur is that, or not cur, or cur, I'll just say not cur. Oh, it does not like that. Cur equals none. Go. And then for cur in dot, oh, can I give it a type? Oh, yeah, give it a type. Python. Can I give it a type, please? Q type Python. I didn't do that. I don't think so. So I'll just say q dot connections. I'll just say q dot append connection. And do I have to do anything else? I just need to make sure I actually added to the queue correctly. It's append, right? Yeah, it is appended for a deck. Okay, nice. And then I'll just print per dot water level. And I'll just give it a name for sakes. Yeah, we'll just give it a name for fun. Or I'll just give it an ID, whatever. There you go. So down here, we'll just print cur.id, cur water level. Then we'll here the node, we'll make no connections, we'll give the ID of 0. And then we'll go down here and we'll call it DFS or BFS on our graph. It crashed. Why'd you crash, buddy? None type object is not iterable. Oh, yeah. Oops. Connections, this is equal to this by default. And this is equal to -1 by default. There you go. Okay, no, you're still mad. Cur.connections, none type is not iterable. Okay, how about you comment all this out and you say this. Okay, 0, 0. There you go. Okay, so why is none type not iterable? I mean, obviously, right? Shouldn't it not go through because connections is null? Oh, because I'm overriding the value. There you go. Alright. Okay, so here we go. Let's just make a simple case. So, have your graph. Maybe we're connected, this is like our source node, this is connected to this one, which isn't connected to anything. Node 3, which node 3 is connected to node 4. I know this looks like terrible, but like, you get it. So the BFS would be, and then as we were to add, I would want to print connection dot ID. And then end is equal to this. Or actually what I can do is I can just do I can technically, if I want to print out the level, I can just do For simple case, I'll just say level. Let's do this. Actually, I don't actually need to do that. Let's just go down here. We'll just say print on.id and leave it with space. There you go. Then obviously after you finish the BFS, print on every new line, you print a new line. There you go. So on level 1 you get 2, 3, and then on level 2 you get 4. And then let me say end is equal to nothing. Oh wait, what? I just want to print a new line. Why is it being so weird? That's not gonna be here where I want. I'll just do that. So level 1, 2, 3, 4, okay. And at the start, we'll print starting, and then we'll say node.id. There you go. Oh. And we'll just do that. There you go. Clean. 1, 2, 3. That's actually weird. Why is it spaced like that? But whatever. So you start at 1, you go to 2, 3, and then you go to 4. Because they're all on different levels. Because the way this looks like is you have. Alright. Now. Now we have a basic connection. But we have no information about those connections. Right? And also, each connection isn't bidirectional because they don't connect back up to the parent. Right now, they're only one directional. Because what happens on node 1 when we say, hey, we're going to go to node 2, node 2 doesn't know that it's connected to node 1. Has no idea about that. Like, really, literally no idea. So, to make sure it has knowledge of its parents, you can pass in its parent. Which is a node, is how you put a type. No. Okay, well, it's a parent, which is equal to none by default. And then basically what we need to say is we need to add the parent to the connections list. How do I expand this? Can I do that in Python? Oh, it doesn't like that. Can I do that? Oops. I want this to like split apart. Like I want to now to append an array to another array, but keep it flat and Python. Oh, I can literally just say, oh, connections dot extend parent. Oh wait, what am I doing? Connections dot append parents. The hell? Oh wait. No, you don't do it right there, but you can do it right there, and then I'll say, and then down here before I finish, I'll say self dot connections dot append parents. This returns none, and this is an array list node. Ooh, does not like that. This is a node. How do I do that while also giving it a default type? Why is it throwing error at me? Non-default arguments follows default argument. Oh. What is it? Int for Python? Int this node. Why are you upset? This is not defined? Oh, chill out, bro. And then if I say none, if I say this, if I say -1, you work. No, you still don't work. Oh, it's because I put a capital L. And then why is it not like this? Or I'll just say self. Wait, does it like if I say self? Whatever, it's not important. Just make sure it's a list. Just make sure it's a list. Make sure this is a parent or node. Will it actually crash if it's like that still? Yeah, it will be. Whatever. I'll just do this. It doesn't matter. Doesn't matter what type it is. Doesn't matter that. Okay, ID. Yep. Whoa. What happened? None type object has no attribute ID. Oh, return self. Yeah, no, I don't have to return shit. Fuck you. Oh, what? Whatever, it doesn't matter. Python types and constructor. Okay, no one's telling me how to do it. I don't understand why it's showing this error. So I will. I have no idea why it's showing this error because that does exist. Which this list should be a type of how to give type of a variable of itself in a class in Python. Oh, capital self. No. The fuck? Okay, I don't understand why it won't do that, but as it won't do that, what we'll do is just default to that, default to this, default to none. Okay. Oh, because parent is none type. I'll just say if parent. There you go. That's why that was happening, and then I can actually give these types back. Alright, list. Whatever. Yeah, okay. I don't know how to do that, but I don't care. There you go. If parent, 10, obviously. Now these are connected. Now, for this, can't really do this anymore. So we'll have to say, okay, so I'll just do, x1 is equal to node 1. x2 is equal to node 2. x3 is equal to node 3. I know this is not very the most efficient, but I'm just testing this out. Okay. Now our graph will be equal to node 1. Okay, so which here, what we'll do is we'll do, I need to do this, paste this here, there you go. This all needs to be in opposite direction. So x3 is equal to node 3, x4 is equal to node 4. You make a more efficient way to construct this graph, but for now it doesn't matter. X2's parent is x1. Okay, so here its parent is x3. Nothing. Oh, yeah, it doesn't know that, though. Oh my goodness. Here's what I'll do. Class graph. There you go. Define its self.graph is equal to this. Define add node. Self and node should be this. It actually knows its type now, which is good. And it will say if node not in graph, we'll say is self.graph dot at node will equal this. We'll say define add edge, which will take in a self a I'll just do it by ID, node ID. Ooh, how do I want to actually say this? Should I store it via ID or should I store it via node? I'll just store it via node, so node source, which is a node. A1. What should the parameter be called? From node to node. If self.graph if from node in self.graph dot from node dot append to the to node. Oops, node. Else in the graph, we'll just add it itself, which is from node that's equal to node. Go. Now we just have a print graph function. Print or oh yep, it's gonna get mad at me because that's x4 and on C in self.graph items say print n to C. Go. Now what I can do is I can say graph or graph is equal to new graph. The graph dot add edge. And then now we actually don't need to keep a list of these connections anymore. This node can just keep its own value. And what we can say is, I mean, honestly, I could have just created nodes and then I could have done it in an adjacency matrix from the start. How do I want to do that? Because that's technically just saying adjacency matrix, but with just a shit ton of functions. Whatever. graph.addEdge, node ID 1, which can connect to node 2. Also add another edge, which, oh fuck. Problem is, it's gonna create like a new instance of itself, which will be an issue. What I'll do now, I think I'll just store the graph via its ID, point to the actual value. Well, the thing is what you're supposed to do is, what I could do is, here's what I'm thinking, because this is kind of annoying, because what I'll have to do is I have to clear all the variables and then add all the edges, because like these keys aren't unique. So what it's doing is it's storing the node itself, but when I create a new node, it's going to give it new memory and everything. So it's not going to be like its own key. Right? So like this, I can't just say node 1 and then add another connection. I have to like actually store all these in a value. So I need like a unique identifier, which like an integer or a string, where I can kind of just reference it. Question is, how do I want to structure that? What I can do is I can for easy searching, I could just have a map here which stores all the nodes. For keeping track of the connections, I'll just obviously do what I'm doing right now. So we'll say self.nodes is equal to this. We can also do also we can say from arrive default. There you go. So I want to actually make this a default div of a list of there you go. This can be a default div of fucking this doesn't need to be default div, to be honest. Now I can switch this around and stuff, so I can say add node. There you go. I can just keep that. But adding an edge, what I can say is now this should be an ID, which is int. Now if ID not in there, we say ID is equal to that, right? Because this is basically your connections. And then what we need to do is we need to also say and ID not in self.nodes. I mean, obviously it won't be because there's going to be a case where that happens, but let's just check. Self.nodes at ID is equal to, actually we'll take in a node, which has to be a node. Then we'll go down here and we'll say node.id, that, down here, and node.id, there you go. There you go, there you go. Alright, now at node.id, you can initialize that, and then here we can say node.id is equal to node. Go, so that adds it. Now when we add an edge, we can delete this, we can delete this, we can delete this, there you go, that's all you do. So from node, there you go, this needs to be now int. 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 From to node, you keep track of it like that, you print this, which this we can just say self.nodes at this is equal to ID. Oh, I mean, we don't actually have to say that because it's going to print the baby anyways. Now we create the graph. We add an edge. We can have two edge functions. Which is from node, we're taking a node, and then to node, taking a node. And then if not from node in nodes, and to node, or to node in nodes, which basically means if they are both not in the graph, which basically just means if from node, if self.nodes and self.nodes, actually, how do I want to take care of this? If self.nodes from node, this is not the case, we can just say self.nodes dot, and we're at from node ID is, what the hell? Why is that not working? What the hell? Why is my keybind not working? That's a little annoying. Oh, because my caps lock was on, that's why. And then if not self nodes to node, say self.nodes from node dot to node node. Alright, here, wait, what am I doing? Bruh, I'll just say, add node, self.add node, just add the from node, self.add node, from the to node, and then just do self dot oops, the tab is messed up. Self dot add edge, and you just say from node dot ID, and then to node.id. Why does this work? Well, add node automatically prevents duplicate IDs. So we are not creating extra space list. And then here, and the edge. So now, if I call this add edge, what will happen is it'll actually add the edges correctly. And we can start this BFS from the graph dots nodes at 1. Oops. Oh, sorry, I did not see your chat. My chat was closed. Next time I'll probably start doing leak code problems again. We'll honestly, I mean, I can do them anytime. I don't care. Probably do them tomorrow, so. It's just I stopped my competitive programming thing, so I was like, there's no point in like sharing my progress like that. But int object has no property ID. Oh yeah. Return a I changed it. Change con because now they're issue here. Alright, sorry guys, I haven't been talking, but let me get back into this. We're having an issue. Basically, I'm just creating this graph class for us to navigate this effectively. However, I suck at coding and I'm having an issue. If node.id, where was that at? weird. Int object has no attribute ID. Why is this getting passed as an int? It literally says pass in as a node. The fuck? What, wait, which one is this getting passed in by? Does it know to overload it? Yeah, it does. What the fuck? It doesn't know to overload it. Nice. So I was digging around. Where's this getting used at? Oh. There you go. Alright, nice. Okay, so now I just need to make it bi-directional. And to make it simple, let's just make this a fucking set. I'm pretty sure I don't have to do this, right? Yeah, I do. Nice. And then let's make this a set so I know how to make duplicates. And the reason why I'm doing that is because, oh yeah, it's gonna crash. But the reason why I'm doing that is because I want to make it bidirectional and to make it really simple. I'm just gonna say every time you add an edge, you will just add the parent itself to it. And then since it's a set, it won't actually fuck with itself. So I'll just say self.graph.add to node, and then we'll say .add from node. There you go. And now it's mad because it's not iterable. Oh, that's kind of annoying because I actually would want that to be iterable. Oh, what the? No, fuck you. A set is iterable. What do you mean? Oh, it's because I did this. Oh, I'm an idiot. There you go. Yeah, so 1 goes to 2, goes to 2, goes to 1. Boom. Yeah, nice. Simple. Now since it's set, it won't freak the fuck out when I say this logic. And then I want to fix this logic too. Okay, that's done. And then I'll change this to just add edge because that's probably what I'm going to be using the most. There you go. So our graph class is made. Now, let's make sure the BFS still works. It does not. It actually shit the bed. So, why did it shit the bed? Because the connections are actually equal to graph dot get at curve. Those are actually its connections. Oh wait, this returns a node. Get a connection. I'll name this get node. And then what we can just say is self dot ints, just return a list. It's simple. Alright, let's make this a list so returns a list. Sorry I'm not talking very much, guys. I'm kind of doing something right now. What type is curve? Okay, so we pass in a node, get connections, and then we can say get connections, we pass in that. And then we could say, we could probably say, so we have cur invis or cur. Or this dot add cur. Or connection in dot get connections, we print that and we say q dot append connection. Okay, it's showing empty sets because why? What is cur? Cur is a node object. There you go. Why isn't? Wait, I thought if you declare types in Python, it would crash if you didn't throw the correct type in. What's the point of all these types if it doesn't crash? Like, I don't need whatever. Okay, well, I'll just say node ID and then it'll fix itself. There you go. Take that. There you go. Don't need to do this anymore. There you go. Oh, it's adding extra space because that. Never mind, I understand now. Okay. So you get 1, 2, and then why is it printing out 1 again? Go to deck. There you go. Current. This is some unexpected behavior. I had that. Go node. Cur is equal to pop left. If cur is or not cur, continue. Else we print the current value we're on. We add it to the visited set. Then we go through the connections. Oh. Yeah. That's why. If not in viz. Or if con in viz. Continue. There you go. Now it should stop. To a certain extent it should stop. I just want to print out the current value I'm searching. Let me add another edge. Graph.add edge node 1 to node 3. And then we'll just say I'm gonna try to stream every day for at least an hour. And today I did 4 hours because I lost track of time. And I actually need to stop soon, so. I just want to create the nodes. The flood simulator I will try to finish tomorrow for anyone watching. I will be back tomorrow. I didn't expect it to be 4 fucking hours, but what are you gonna do about it, I guess. One, two, three. Nice. Okay, finally, this is all done. Now, let's go through. So the BFS is working and we got this. Now we can actually like implement. Now we need to store information about each connection now. So from our solution, basically we stored Which I don't know why I'm so dumb. Maybe tomorrow when I come back we'll be able to figure it out nicely. But basically what we said was, okay, so each node's going to need to know its connection, which we have, and then basically information about that connection. What is that information? Well, we want to store the depth, which is how far it is away from the source node, which I will do later. And we just want to store the height it should be at. So the height of the connection, which we can add to our add edge statement. Hello, Oreo. So in our graph, which is basically this, we need to store more than just a, well, we can store a set that tells you the, so basically what we're going to need to do is we're going to need to store information about that connection. An issue we're having right now is the problem is right now I'm just storing the IDs of all the other nodes that exist, but I'm not storing any information about their connection. This is actually going to change the functionality about our connect, or like how I'm currently storing this in the graph, because it's just a set and it's like, oh, okay, well, this is this ID, but I actually want to just store, I don't know if I want to do like I want to do a map where I could, I think that might be a little crazy though, where I could do a map and then I just store, just map it to this, so I could just say 1 and then 2. Yeah, actually, that sounds like a good solution. So what I'll do up here is I'll just create a class called connection data. Define init, which will be the source. It'll be their ID. And a destination, which is int, which is their ID, right? So let's say source ID, destination ID, and then we'll say water level. So I mean, technically, all I would have to technically add would be I'm actually doubting this. Do I need a whole ass class for this? Because it's just, I realized that all we're storing is the water ID, or like the water level, which is the water level you need to reach that node. does this really matter? Nah, for now, what I'll do is I'll just comment this out, and I'll just make this a, not a set, but just a, okay, now you, I don't want to do that, it's all so stupid, but, the graph is equal to a default deck, which then has, which I would just want to map it to a certain water level that it has. But I need to store the Alright guys, okay. I think here's the issue. The issue is I've been streaming for 4 hours and 30 minutes, and I haven't took a single break. So I'm completely brain farted. Like, it's over. So I'm gonna end the stream. It was a good stream. Again, like last stream, a lot longer than I expected it to take. I did not expect here, let me try to use it. I did not expect it to take 4 hours and 30 minutes, and again, not to finish the project. Not even this time, not even close. At least the last time I was close to finish the project. This time, hell no, not even close. Not even close at all. However, we're gonna come back to this. I really do want to finish this. I'm gonna come back to it. I want to work on this off stream for a little bit, so I can come on and like actually show you guys this stuff. The current, we figured out literally most like 90% of the whole thing. We just need to figure out this one edge case, which we discussed earlier in the stream. We just need to figure this out. Maybe I'll look it up. I don't really want to, but yeah, I think I still have a chance on figuring it out myself. But or maybe I could ask a friend. But yeah, we just need to figure that out. Once we figure that out, I mean, coding it is easy because all it is just it's just graph traversal. That's not too hard. The only reason why I'm taking so long to do it is because I want it to like at least be a little bit clean. But if I just wanted it to be really dirty, I could I could whip it up in a little bit. So like literally all we have to have left is just to figure that one last edge case, and then we'll be good to go. So thanks for everyone tuning in the stream, staying in, trying to help out or just watch or whatever. I'm gonna be trying to stream every day for at least an hour. Yeah. You should probably, yeah, that'd be a good idea to go to sleep. But yeah, so I'll probably be back tomorrow. If not tomorrow, definitely the weekend, and hopefully we can get this thing done by the end of the weekend, like for sure. So yeah, so I'll see you guys. Stay tuned for some more, and